Across the vastness of space, beyond the stars we know, exists a galaxy. One that has captivated the imagination of scientists, explorers, and dreamers for centuries. A galaxy that stretches 2.5 million light-years across the cosmic expanse. A galaxy that is older than our own, yet still evolving, still growing, still full of mysteries waiting to be uncovered. Welcome to the Andromeda Galaxy, known to us as M31. This immense spiral galaxy has witnessed the birth and death of countless stars, the formation of planets, and the endless dance of cosmic forces. It is our nearest galactic neighbor, yet its distance from Earth is so vast, it feels almost unfathomable. And yet, it calls to us. What is hidden within its spiraling arms? What secrets does it keep at the core of its being? Could it hold the answers to the greatest questions we've ever asked about life, the universe, and everything within it? Stand on the edge of space and look across the void at this distant galaxy. What would it be like to travel to this faraway world? To venture across the stars, through the emptiness of intergalactic space, and witness the impossible? To see the stars born anew, to understand the forces shaping the very fabric of our universe. Now, visualize taking a journey like no other. A journey not through the boundaries of our solar system, but one that takes us to the very edges of the known universe. A journey to the Andromeda Galaxy. A journey into the heart of the unknown. It would take time beyond comprehension. It would take technology beyond our reach. But if we could travel to Andromeda, what would we discover? And what might it teach us about the future of humanity? For 1,000 years, humans have gazed up at the night sky, wondering what lies beyond. And as we peer into the cosmos, we find ourselves drawn to the mystery of Andromeda. But this isn't just a story about stars. It's a story about us. It's a story about the universe unfolding, revealing its secrets one galaxy at a time. And it's a story of the future, of what could be, of what we might one day become, if we can unlock the cosmic gates that separate us from the stars. Are we ready to take the next step in our cosmic journey? To leave behind the familiar and venture into the unknown? To cross 2.5 million light-years and stand at the doorstep of another galaxy, one that holds the key to understanding everything about the universe and, perhaps, ourselves? Join me now as we embark on an unforgettable journey. A journey to the Andromeda Galaxy. A journey that will take us through the heart of space, through the limits of our imagination, and into the very core of what it means to be human. Prepare yourself, for this will be a voyage that will change the way you see the universe forever. Stay with me as we set forth on our journey to the Andromeda Galaxy. Chapter 1. The Birth of Andromeda, a Cosmic Genesis. The origin and history of Andromeda. The birth of Andromeda around 10 billion years ago. 10 billion years ago, a vast cloud of gas and dust, scattered across the fabric of space, began to come together. This was the birth of something truly extraordinary. A galaxy, a vast collection of stars, nebulae, and cosmic material was forming. This was the beginning of Andromeda. At that time, the universe itself was only a few billion years old. The stars that lit up the sky were already ancient in their own right, having burned for millions of years. Yet, in the swirling cosmic chaos, Andromeda began to take shape, one of the largest galaxies in the local group, a collection of galaxies bound by gravity, including our own Milky Way. From this cloud of interstellar matter, the first stars began to emerge. Their formation marked the beginning of a new era. The dense regions of the gas and dust collapsed under the force of gravity, igniting the first nuclear reactions and creating the first stars. Bright, powerful, and full of energy, these stars, each one a miniature furnace burning with incredible heat, began to push the remaining gas and dust out of their immediate vicinity, leaving behind clear paths where new stars would be born. This process, one that repeats itself over and over in galaxies across the universe, marks the birth of Andromeda. The gravity from these newly formed stars began to pull in more material, growing the galaxy. As the stars gathered, they formed clusters, which merged into larger groups, shaping the galaxy's spiral structure that we see today. It wasn't an instant process. It took millions of years, vast stretches of time that allowed Andromeda to evolve and grow into the behemoth we now observe. Andromeda, like all galaxies, had to go through various stages of growth. At first, the galaxy was a chaotic swirl of gas, dust, and newborn stars, each one pushing and pulling on the other, guided by the invisible hand of gravity. Over time, the structure began to solidify, forming a central core, around which stars would orbit, eventually giving birth to spiral arms that stretched out from the center. As stars continued to form, the galaxy began to stabilize. The gas that was once scattered throughout Andromeda was now being pulled into dense clumps, turning into new stars and clusters. Meanwhile, the stars that had already been born drifted in intricate orbits, contributing to the galaxy's growing complexity. But this early version of Andromeda was not static. Like all living systems, it evolved. It collided with smaller galaxies, absorbed their material, and grew larger and more complex. Each collision, each merger, pushed the galaxy to change, to become something new. Over billions of years, Andromeda would evolve from a simple, chaotic nebula into the majestic spiral galaxy we recognize today. The first hints of its spiral shape began to emerge as the stars started to settle into more stable orbits. These early spiral structures were not the smooth, graceful arms we see today, but rather rough, irregular swirls of stars and gas. The galaxy was still in its infancy, still in a constant state of motion and turmoil. As the stars continued to form, they began to shine brighter, casting their light across the cosmos. This light traveled through space, stretching across billions of miles until it reached distant observers, like us. The light that reaches our eyes today is a relic of the past, a snapshot of Andromeda at a particular moment in its evolution. Over time, Andromeda continued to evolve. The galaxy's core grew denser, and the formation of new stars slowed. Instead, the gas and dust that were once plentiful began to be consumed, leaving behind the stars that formed the backbone of the galaxy. And the spiral arms, those elegant curves that we associate with Andromeda, grew sharper, more defined. But it wasn't just the stars that made Andromeda so captivating. It was also the forces at play within the galaxy. The supermassive black hole at its center, still hidden in the heart of Andromeda, was already beginning to shape the galaxy's structure. This black hole, millions of times the mass of our Sun, exerts an incredible gravitational pull on the surrounding stars and gas, helping to define the shape and dynamics of the galaxy. As Andromeda continued to mature, its stars began to interact more intensely with each other. Some stars merged, others were flung out of the galaxy's orbit, and some were drawn into the center, where they would eventually be consumed by the black hole. These interactions, this constant dance of cosmic forces, has been shaping Andromeda for billions of years. And it is from this violent, yet beautiful, cosmic chaos that Andromeda grew into the galaxy we see today. A sprawling spiral of stars, gas, and dust, wrapped in elegant arms that stretch across the cosmos. It is the product of billions of years of evolution, of cosmic forces working together in harmony and in conflict. And even now, Andromeda continues to evolve, its stars being born, living, and dying, creating new elements, new planets, and new stars with every passing moment. This is the story of Andromeda's birth, an incredible journey that began nearly 10 billion years ago and continues to unfold before our eyes. It is a story of cosmic forces, of creation and destruction, of star births and galactic collisions. And this story, while ancient, is far from finished. How it formed alongside the Milky Way, highlighting its similarities and differences. Roughly 10 billion years ago, Andromeda and our Milky Way were both taking shape in the early universe. As the cosmos began to cool, clouds of gas and dust coalesced, driven by gravity, slowly forming the building blocks of galaxies. While Andromeda was forming in one corner of the cosmos, the Milky Way was also beginning its journey on the opposite side of the universe. They were destined to become the largest galaxies in the local group, two galaxies that share a similar history but are distinct in their own way. Like the Milky Way, Andromeda was born from the collapse of a massive cloud of gas. This cloud, filled with hydrogen and helium, became dense over time, triggering the birth of stars. Stars began to form in clusters, and the galaxy's structure began to emerge. The formation of Andromeda mirrored that of the Milky Way, as both galaxies followed a similar evolutionary path, driven by the same universal laws of physics. But Andromeda, due to its larger size and different dynamics, evolved in its own unique way. While both galaxies are spiral in nature, Andromeda's spiral arms are more pronounced and expansive. The Milky Way's arms are thinner, tighter, and more compact, giving the Milky Way a slightly more compressed appearance. Andromeda, by contrast, boasts a grander structure, with arms that stretch far into space, a visual testament to its larger scale. These arms of Andromeda are rich with young stars, stellar nurseries, and nebulae, regions where new stars continue to be born. Though both galaxies share similar elements, stars, gas, dust, and dark matter, the way they are organized and interact is where the differences become clear. The Milky Way's structure is relatively flat, with a clear disk surrounded by a halo of stars and dark matter. Andromeda, on the other hand, has a thicker disk with a prominent bulge at its core. Its spiral arms stretch out much farther, and the central region is more crowded with stars. The bulge in Andromeda is much larger than that of the Milky Way, making its core particularly dense. As the stars in both galaxies formed, they began to interact in subtle yet important ways. The Milky Way, with its smaller size, was able to maintain a more stable orbit, keeping its stars relatively close to the galactic plane. In Andromeda, however, the larger scale of the galaxy allowed for more dramatic interactions between stars, particularly in the outer arms where the galaxy's gravitational forces were weaker. But their similarities extend beyond mere structure. Both galaxies contain supermassive black holes at their centers, acting as anchors for the stars around them. These black holes, millions or even billions of times the mass of the Sun, exert an immense gravitational force on their surroundings. The black hole at the center of Andromeda is as mysterious as it is powerful. Though it is not as active as some other black holes in the universe, it has a profound influence on the galaxy's evolution. While both galaxies evolved through similar stages, they took different paths after their initial formation. Andromeda has been a more active galaxy throughout its life, experiencing a greater number of star formation events. The abundance of gas in Andromeda helped to fuel these processes, allowing for the creation of new stars at a rapid pace. On the other hand, the Milky Way, although it has seen its own bursts of star formation, has been less active in recent times. Most of its gas has been used up, and star formation has slowed significantly. The interactions between these two galaxies were inevitable. Andromeda, larger and more massive, has always had a gravitational influence on the Milky Way, pulling at its stars, gas, and dark matter. Over time, these two galaxies have gradually drifted toward each other, pulled together by their mutual gravity. This slow, inexorable approach will ultimately lead to their collision, which is predicted to occur in about 4 billion years. Despite their differences, Andromeda and the Milky Way share a profound connection. Their histories are intertwined, and in the distant future, they will merge to form a single, massive elliptical galaxy. This collision will reshape both galaxies in ways we can barely imagine. But for now, they continue to coexist, two grand structures of stars, gas, and mystery, each telling its own story of cosmic evolution. Though Andromeda and the Milky Way may seem very different in their structures and evolution, they are bound by the same forces. Gravity, the relentless pull that shapes all galaxies, is what has shaped these two giants. And while their fates may differ in the distant future, their stories remain deeply connected. As both galaxies continue their journeys through space and time, deep dive into the history of the galaxy, how stars, planets, and other celestial bodies came into existence in this massive spiral galaxy. As Andromeda began to take form over 10 billion years ago, it became a crucible for the creation of countless stars, planets, and cosmic structures. In the vast darkness of space, an immense cloud of gas and dust, primarily hydrogen and helium, began to collapse under the force of its own gravity. This collapse was the first spark, the beginning of a process that would give birth to everything we know in the galaxy. In the earliest stages of its formation, Andromeda was little more than a massive, swirling cloud of gas. As gravity pulled these particles closer together, the cloud began to heat up. And when the gas reached a critical density, nuclear reactions began. These reactions marked the birth of the first stars, massive, bright, and scorching with heat. This was the moment that marked the true beginning of Andromeda as a galaxy. These newborn stars formed in clusters, with hundreds or even thousands of stars coalescing in tightly bound groups. In the core of these star clusters, nuclear fusion powered the stars, creating an environment where new elements were forged. Elements like carbon, oxygen, and iron were created in the hearts of these stars, elements that would one day become the building blocks of planets, life, and all of us. As these stars continued to shine, they began to shape their environment. Intense radiation from these young stars pushed gas and dust out of their immediate vicinity, creating a more defined structure in the galaxy. This process not only cleared space for new stars to form, but also created the delicate balance between star formation and the depletion of the interstellar material needed for new stars to be born. Alongside these stellar nurseries, massive clouds of gas and dust began to cool and condense, eventually forming the raw material for planets. The regions of space within Andromeda that were rich in gas became the birthplaces of planets, moons, and asteroids. Just as they did in our Milky Way, these planets, like the stars that preceded them, formed through the slow accumulation of material. Small particles collided and merged, growing into larger and larger bodies, eventually becoming fully formed planets. But not all of the material in Andromeda's vast clouds went into forming stars and planets. Much of it remained in the form of dark matter, an invisible substance that makes up the majority of the galaxy's mass. This dark matter doesn't emit light or radiation, making it invisible to us, yet its gravitational influence is undeniable. It anchors the galaxy's stars and helps to bind Andromeda together, ensuring its structure remains stable over time. As Andromeda's stellar population grew, the galaxy began to take on more complexity. Some stars, particularly the older, more massive ones, burned through their fuel quickly, reaching the end of their life cycle faster than others. These stars exploded in violent supernovae, releasing tremendous amounts of energy. The material from these explosions, rich in heavy elements, was scattered into the surrounding space, enriching the galaxy with the building blocks for future generations of stars and planets. The remnant cores of these exploded stars formed neutron stars and black holes, objects so dense and powerful that their gravity could not be escaped. These black holes, especially the supermassive one at the heart of Andromeda, exerted a profound influence on the galaxy. They acted as a gravitational anchor, pulling in stars and gas, shaping the galaxy's overall structure, and providing the energetic pulse that would eventually fuel the future of the galaxy. Over billions of years, Andromeda stars continued to evolve. Some formed in the bright, energetic spiral arms, while others were older and had drifted into the galaxy's central bulge, where they moved in more circular orbits. This dynamic motion, this dance of stars, gas, and dust, continued for billions of years, shaping Andromeda into the majestic spiral galaxy we see today. But star formation wasn't the only process at play in Andromeda. The galaxy also grew by absorbing smaller galaxies and the remnants of cosmic collisions. These galactic mergers were frequent early on in Andromeda's life, and each collision brought new material, gas, dust, stars, into the galaxy, fueling further star formation and expanding its reach. These collisions not only shaped the structure of the galaxy but also affected its motion. As Andromeda absorbed smaller galaxies, their stars and gas became part of its larger system, adding to its growing mass and complexity. Andromeda's size and mass grew over time, and as the galaxy's core grew denser, the stars within it began to interact more dynamically. Stars near the core were pulled into more elliptical orbits, and some were even ejected from the galaxy altogether. This constant interplay between stars, gravity, and material gave rise to the distinct features that define Andromeda today. Its spiral arms, its dense central bulge, and its dynamic interactions between the stars and the supermassive black hole. Even as Andromeda was growing and evolving, the gas within the galaxy began to settle. It began to form dense clouds, which would eventually become the birthplace of new stars. These gas clouds acted like cosmic incubators, where conditions were just right for new stars to form. As new stars formed, the galaxy continued to grow, expanding outward in all directions. Each new star that formed in Andromeda came with its own story. Some were born with more mass, burning brightly for millions of years before eventually dying in fiery explosions. Others were smaller, living longer, more stable lives, creating a mix of stellar types within the galaxy. And in these stars, the chemical elements necessary for life were created. Elements that would one day form planets, and perhaps life itself. In this way, the life cycle of stars within Andromeda is an ongoing process, one that has continued for billions of years and will continue for billions more. As old stars die, they create the conditions for new ones to form, and this cycle of birth and death shapes the very fabric of the galaxy. And while many of these stars will burn out and fade away, others will be born in their place, ensuring that Andromeda remains a dynamic, living galaxy, forever changing, forever growing. Chapter 2. The Cosmos Through Our Eyes. From Earth to Andromeda. Journey through time and space. How humans first discovered Andromeda through telescopes and early astronomical observations. For 1,000 years, the stars were simply people looked up in awe and wonder, but they knew little about what lay beyond. The great cosmic mysteries, like the Andromeda Galaxy, remained hidden, far from the reach of early astronomers. The telescope, the instrument that would unlock the secrets of the universe, had not yet been invented. The quest to understand the vast expanse of space would begin only when the power of the telescope finally turned toward the heavens. In the early 17th century, humanity's understanding of the universe began to change forever. The invention of the telescope revolutionized astronomy. Galileo Galilei, one of the greatest pioneers of modern science, was the first to turn this new tool toward the stars. His discoveries, which included the moons of Jupiter and the phases of Venus, changed our understanding of the solar system and the cosmos. However, it wasn't until the 18th century that astronomers began to use the telescope to explore the distant reaches of space beyond our solar system. And it was during this time that the Andromeda Galaxy began to make its first appearances in the astronomical records. Early observers, armed with telescopes, started to notice a faint, hazy patch of light in the night sky, a light that seemed to defy simple explanation. This was the first glimpse of Andromeda. One of the first recorded observations of the Andromeda Galaxy came from the Persian astronomer Abd al-Rahman al-Sufi in the 10th century. He described the Andromeda Galaxy as a small cloud in the sky. However, his observations were not based on modern telescopes. It would take centuries before astronomers had the tools necessary to truly unravel the mystery of this faint, distant object. By the 17th century, astronomers like Johannes Kepler and Isaac Newton had developed the mathematical and observational tools needed to better understand the movements of celestial bodies. While they were focused on planets, moons, and the laws of motion, the faint smudge of Andromeda continued to beckon from the depths of the universe. Then, in the early 19th century, the advent of larger and more powerful telescopes allowed astronomers to examine Andromeda in greater detail. One of the most significant figures during this period was Sir William Herschel, who used his massive 40-foot telescope to scan the night sky. Herschel cataloged thousands of stars and nebulae, and his observations of the Andromeda Galaxy helped establish it as one of the most significant objects in the sky. Herschel's work led to the idea that Andromeda was a nebula, a cloud of gas and dust within the Milky Way. It wasn't a galaxy in the sense we understand it today, at least not yet, but it was the first step in realizing that the universe was far more complex than previously imagined. His observations, while groundbreaking, were still limited by the technology of his time. But they set the stage for the next generation of astronomers to make a discovery that would forever change humanity's understanding of the universe. As the 19th century progressed, advances in telescope technology brought even greater clarity. In 1845, Lord Rosse, an Irish astronomer, observed Andromeda through his enormous, state-of-the-art telescope. Lord Ross's observations were among the first to suggest that Andromeda was not just a nebula, but something far grander, a distant, rotating spiral system, unlike anything seen before. He described Andromeda as a spiral nebula, a term that would linger in the minds of astronomers for years to come. But despite Lord Ross's groundbreaking observations, the true nature of Andromeda remained a mystery. Many astronomers of the time, including Herschel, believed that Andromeda was a cloud within the Milky Way, not a separate galaxy. It wasn't until the 20th century that humanity would definitively discover that Andromeda was an independent galaxy, one of the largest in the local group of galaxies. Enter Edwin Hubble, the American astronomer whose discoveries would forever change our view of the universe. In the 1920s, Hubble used the newly constructed Hooker telescope at Mount Wilson Observatory to peer deeper into Andromeda than ever before. Through the power of this telescope, Hubble was able to observe individual stars within the Andromeda Galaxy and measure their distance from Earth. It was here, in the quiet stillness of the observatory, that Hubble made his groundbreaking discovery. Hubble showed that Andromeda was not a nebula, as previously thought, but a galaxy entirely separate from our own Milky Way. He calculated that Andromeda was located 2.5 million light-years away, an almost incomprehensible distance. And with that, the universe, once confined to the Milky Way, suddenly expanded. The Andromeda Galaxy was no longer just a distant smudge in the sky. It was a massive, independent galaxy, one of the closest to our own. This discovery was monumental. It shattered the prevailing belief that the Milky Way was the entirety of the universe. Andromeda, as a separate galaxy, opened the door to the realization that there were countless other galaxies beyond our own. Hubble's work not only established Andromeda's place in the universe, but also laid the foundation for modern cosmology. His discovery of the true nature of Andromeda was a pivotal moment in the history of astronomy, forever altering humanity's perception of its place in the vast cosmos. Through the work of these early astronomers, Galileo, Kepler, Herschel, Lord Ross, and Hubble, the mystery of Andromeda was gradually unraveled. From the first tentative observations to the eventual confirmation of its status as a separate galaxy, Andromeda's discovery marked a turning point in human understanding. It was no longer a vague, distant object in the sky, but a galaxy, one of billions in the vast expanse of the universe. Progression of technology and Hubble's breakthrough. Centuries ago, humanity looked upward with wonder but lacked the means to reach beyond the limits of the visible sky. Knowledge was confined to the eye's ability to track motion. The stars appeared fixed. The planets moved in loops and curves. The cosmos was a canvas of mystery with no tools for clarity. That began to change with the lens. The telescope transformed speculation into science. The first crude devices, constructed in the early 17th century, magnified the heavens only slightly, but their potential was profound. Over time, glass was shaped more precisely. Mounts became stable. Observatories were raised on hillsides to escape the thick air of cities. Each new version of the telescope stretched the limits of sight further into the unknown. The refracting telescopes of the 17th century were surpassed by reflectors, which used mirrors instead of lenses to gather light. With this leap, astronomers could study fainter objects, darker regions, and more distant light sources. What had once been faint, featureless blurs now revealed structure, brightness variations, even rotational motion. The deeper into space they looked, the further back in time they peered. By the 19th century, the use of photography changed the pace of progress. No longer relying solely on the human eye, astronomers began recording observations with photographic plates. These long-exposure images collected faint light that no eye could detect. For the first time, permanent records of the sky allowed for precise comparisons over time. Light trails, supernovae, star clusters, once fleeting, were frozen for study. The development of spectroscopy further expanded understanding. By splitting light into its component colors, astronomers began to decode the chemical makeup of stars and galaxies. Different elements left distinct fingerprints in the spectrum, allowing scientists to identify gases, temperatures, and compositions of objects too far to ever touch. These tools didn't just show what things looked like, they revealed what they were. Then came the turn of the 20th century. The Mount Wilson Observatory in California began operation in 1904. It would become the setting for one of the most groundbreaking discoveries in human history. The 100-inch Hooker telescope, the largest of its kind at the time, was installed on the mountaintop in 1917. It allowed astronomers to study celestial bodies with a resolution and depth never before possible. And one man would use it to reshape humanity's place in the universe. Edwin Hubble was not the first to observe the Andromeda Nebula, but he was the first to prove it was something more. In 1923, while analyzing photographic plates from the Hooker telescope, Hubble identified a type of star called a Cepheid variable within the Andromeda Nebula. These stars are unique. Their brightness fluctuates in a way that directly relates to their intrinsic luminosity. By measuring how their light changed over time, Hubble could calculate their true distance. His measurements shocked the astronomical world. The Cepheids in Andromeda were far too distant to be part of the Milky Way. The numbers could not be reconciled. The only conclusion was that Andromeda was not a gas cloud within our own galaxy, but an entirely separate island of stars, another galaxy altogether. This finding dismantled the prevailing model of the universe. Up to that point, most believed the Milky Way encompassed everything that existed. Hubble's measurements shattered that belief. The universe was no longer a single galaxy surrounded by mystery. It was a vast ocean filled with billions of galaxies, each one with its own stars, systems, and stories. Hubble's announcement in 1924 was more than an astronomical statement. It was a philosophical rupture. The Earth had already been dethroned as the center of the solar system centuries earlier. Now the Milky Way, too, had lost its centrality. Andromeda was no longer a cloud on the edge of our galaxy. It was a colossal structure, equal or larger in scale, occupying its own territory in space. The telescope had become more than an observational tool. It had become a bridge between Earth and the cosmos, allowing humanity to cross the boundary of assumption into the realm of measurable truth. Hubble's methods, photographic imaging, Cepheid analysis, careful calibration, would define a new era of precision cosmology. But this revelation didn't come without resistance. The idea of a universe populated with galaxies challenged centuries of thought. The scale of it demanded a recalibration of distances, time, and cosmic history. Hubble's data was scrutinized. His conclusions were debated. Yet, as more evidence piled in from other astronomers, from newer telescopes, from deeper analyses, his discovery held firm. The debate shifted from whether Andromeda was a galaxy to how many galaxies there might be. The breakthrough also launched the concept of an expanding universe. Hubble would later go on to study the redshift of galaxies, the stretching of light toward longer wavelengths as galaxies move away from us. These measurements formed the basis of Hubble's law, a cornerstone of Big Bang cosmology. But before that theory could emerge, the confirmation of Andromeda's galactic status had to come first. That moment was the pivot. The transformation in astronomical thought did not end with Hubble. His discovery inspired a surge of technological development. Telescopes grew in size, in sensitivity, in reach. Ground-based observatories were constructed at higher altitudes. Instruments were adapted to capture wavelengths invisible to the human eye, radio, ultraviolet, X-ray, infrared, each unlocking new views of the universe. Decades later, the Hubble Space Telescope, named in his honor, would be launched into orbit free from Earth's atmospheric distortion. It would capture detailed images of galaxies billions of light years away. Yet the root of this expansion and capability traces back to that first photographic plate, to that Cepheid variable in Andromeda, to the moment when human understanding broke through a cosmic boundary. The galaxy that had once been thought to be a ghostly mist was revealed as a vast star system, and in doing so, it redefined the map of existence. Technology had not only sharpened our sight, it had reoriented our place in the cosmos. How modern telescopes continue to reveal more about Andromeda. When the Hubble Space Telescope was launched into low Earth orbit in 1990, it carried with it more than just cameras and instruments. It carried decades of anticipation. At the heart of that anticipation was a question that had followed astronomers for nearly a century. What else is hidden inside the Andromeda Galaxy? Hubble's placement above Earth's atmosphere eliminated the distortion that had limited ground-based observatories. For the first time, astronomers could see into deep space with unprecedented sharpness. The detail was staggering. No longer was Andromeda just a bright, swirling object in the sky. It became a structured world of billions of stars, all captured in high resolution. What had once been a cloud of light now resolved into individual suns, clusters, and lanes of dust stretching like rivers across space. With each orbit of Earth, Hubble sent back images that dismantled prior assumptions. Massive regions of star formation were found. Supernova remnants were identified with pinpoint clarity. Gas clouds in motion were charted and analyzed. Dark lanes dividing the spiral arms were studied for their density and composition. For every answer, two new questions appeared. Andromeda was not static. It was active, alive, evolving. Infrared and ultraviolet sensors on board Hubble revealed layers invisible to the naked eye. In ultraviolet, Andromeda's hot, young stars stood out in sharp contrast to its cooler, older stellar population. In infrared, the galaxy's dust structures were laid bare, allowing scientists to see through the opaque regions that once concealed entire star-forming complexes. These observations helped researchers map not only where stars are, but where they are being born. The Pan-Andromeda Archaeological Survey, conducted with the help of Hubble and other modern observatories, allowed astronomers to map the galaxy's halo with exceptional detail. This halo, composed of ancient stars and dark matter, wraps around the visible disk of Andromeda like a loose shroud. The survey uncovered streams of stars that had once belonged to smaller galaxies, evidence of past collisions that had been absorbed by Andromeda over billions of years. Hubble also played a crucial role in measuring Andromeda's motion. By capturing high-precision images of specific stars across multiple years, scientists calculated the galaxy's trajectory. These measurements showed that Andromeda is on a direct course toward the Milky Way. Though the merger is several billion years away, the motion has been confirmed. Every observation sharpens the estimate. Every measurement brings clarity to one of the most significant future events in galactic history. But Hubble is only one part of a broader modern effort. The James Webb Space Telescope, launched in 2021, added another layer. Its primary mirror, more than twice the diameter of Hubble's, was designed to observe infrared light with incredible sensitivity. Webb's observations of Andromeda are still ongoing, but even preliminary data has expanded understanding. With Webb, astronomers can peer deeper into the dense cores of star clusters, examine the atmospheres of exoplanets in Andromeda's systems, and analyze light from stars that may have formed in the earliest stages of the galaxy's history. Ground-based observatories also contribute to the picture. The Very Large Telescope in Chile, equipped with adaptive optics, corrects for atmospheric turbulence in real time. It has imaged star clusters within Andromeda with clarity approaching that of space telescopes. Meanwhile, the Keck Observatory in Hawaii and the Subaru Telescope have captured wide-field data, mapping large structures like Andromeda's spiral arms and satellite galaxies. Radio telescopes, such as those used in the Atacama Large Millimeter Array, have traced cold gas across Andromeda's disk, mapping the fuel that powers star formation. These surveys show how hydrogen gas condenses into molecular clouds, where gravitational pressure eventually triggers the birth of new stars. These same clouds may also contain the raw ingredients for rocky planets. Surveys conducted using Gaia, the European Space Agency's astrometry mission, have also tracked Andromeda's stars with exquisite precision. By plotting the motion of stars within the galaxy, Gaia has created a dynamic 3D map. These movements tell the story of how the galaxy has grown, how its mass is distributed, and how it interacts with its own satellite galaxies. Through all of this, one thing becomes clear. Andromeda is not a completed structure. It is a system in motion, full of complexity and in constant transformation. What telescopes have revealed is not a finished product, but a galaxy shaped by time, motion, and gravity. The stars are born and die in cycles. Its spiral arms shift and stretch. Its central bulge becomes denser with every gravitational interaction. And through modern telescopes, these processes are no longer theory, they are data. Andromeda now serves as a mirror and a model. By studying it, astronomers test their theories of galactic formation, star life cycle, and dark matter distribution. Each telescope adds a new layer, and each observation refines what came before. The tools are sharper, the questions are bolder, and the answers continue to expand our understanding of what a galaxy truly is. Technology has become our vessel. It carries us across space, from orbiting satellites to mountaintop observatories. With it, we travel not in distance, but in clarity. And with every photon collected from Andromeda, we are granted another piece of the universe's grand design. Measured, recorded, and understood with a precision once thought impossible. The concept of distance in space, Andromeda's position 2.5 million light-years from Earth. Among all the numbers we've ever used to measure anything, few carry the weight of cosmic distance. One of the most staggering figures in all of astronomy is the number tied to the Andromeda Galaxy's location. 2.5 million light-years away. Not kilometers, not miles, not hours or days of travel. Light-years, the language of distance forged for space, where regular measurements collapse under the sheer size of the universe. To understand that number, begin with the speed of light. In the vacuum of space, light travels at nearly 300,000 kilometers per second. That's about 7.5 times around the Earth in 1 second. A single beam of light covers that distance every tick of a clock. Now stretch that speed across a year. Multiply it by the seconds in that year. The result is 1 light year, roughly 9.46 trillion kilometers. And Andromeda is 2.5 million of those units away from Earth. When astronomers say 2.5 million light-years, they don't mean the time it would take us to drive or fly or launch a probe. They mean the time it takes light, traveling at the fastest possible speed known to physics, to move from there to here. The light we receive from Andromeda tonight began its journey before humans painted on cave walls, before cities were built, before written language. When that light left the galaxy's stars, early humans were just beginning to understand fire. This distance makes Andromeda both a neighbor and a relic. It is the closest spiral galaxy to our own, and yet the information we get from it is ancient. We are not seeing Andromeda as it is, we are seeing it as it was, long before our species had formed words to describe the stars. The view is a window through space, but also through time. Every pixel of every image from Andromeda is a message delayed by epochs. This scale requires a new way of thinking. In daily life, we speak of minutes, hours, and days. Across oceans, we count by thousands of kilometers. Across the solar system, we think in terms of astronomical units, one unit being the distance from Earth to the Sun, about 150 million kilometers. But between galaxies, none of those units are useful. Even the largest numbers we use on Earth don't come close. For this, only light years will do. Andromeda's distance isn't a static number either. The galaxy is moving. Space itself is in motion. The light arriving now left 2.5 million years ago, but the galaxy itself has traveled since then. The light is old, but the object it came from has shifted. In fact, Andromeda is on a trajectory toward the Milky Way. The two galaxies are closing in on each other at roughly 110 kilometers per second. In 4 billion years, they will collide. But the light we see today contains no hint of that future. It's a message from a time before that movement was measurable. The vast gap between us and Andromeda challenges more than our senses. It challenges our technologies. No spacecraft made by humans has even left our solar system at 1% of light speed. Even at our most ambitious speeds, the distance to Andromeda makes it unreachable in any practical time frame. A probe traveling at the speed of the Voyager spacecraft would need over 40 billion years to arrive. That's nearly 3 times the current age of the universe. But that doesn't stop us from learning. The space between galaxies is empty, but not silent. Photons travel across it uninterrupted, bringing us data. When we collect those photons, we decode the stories they carry. We map Andromeda's stars. We study its motion. We examine the chemical fingerprints in its light. All of that information comes across a void so wide that it cannot be crossed by matter within any reasonable future. But light makes the journey. The idea of distance at this scale forces the human mind to stretch. It requires new tools, both intellectual and technological. Astronomers use redshift, parallax, variable stars, and standard candles, objects whose properties are well understood and can be used to measure distances with accuracy. The Cepheid variables Hubble observed remain essential tools in the measuring of space. Each pulse from one of those stars is like a marker set down across the great cosmic road. Understanding that Andromeda is 2.5 million light-years away also reframes our place in the universe. Earth orbits a single star in a galaxy of hundreds of billions of stars. That galaxy, the Milky Way, is just one among countless others. Andromeda is the closest large one, but beyond it lie more, farther, fainter, older. To observe Andromeda is to stand on the edge of one island and stare across an ocean toward another. Space is not just about where things are, but when we see them. The distance to Andromeda means we are witnesses not to the present, but to a frame in time locked millions of years in the past. It reminds us that even with the best instruments, we are always looking backward. The universe has already changed since the light was sent. Every observation is a record, not of what is, but of what was. And in that sense, distance becomes memory. Andromeda's stars shine into our night sky, but those photons departed before pyramids rose in Egypt, before the Ice Age ended, before human history began. To observe Andromeda is to receive the echoes of a galaxy frozen in the deep past, still crossing the dark, still arriving. Chapter 3: A Galaxy of Wonders. The beauty and structure of Andromeda. Exploring the Andromeda Galaxy. Focus on Andromeda's size and structure. Look up at the sky tonight, and if you're lucky enough to find a dark patch far from city lights, you'll spot it. A faint smudge of light hanging in the heavens. This is Andromeda, the closest major galaxy to our Milky Way. But don't let its faint glow fool you. Andromeda is a colossal, intricate structure. A barred spiral galaxy whose sheer size and beauty stretch across the cosmos in ways most of us can't yet fully comprehend. To understand the true scale of Andromeda, consider this. It spans about 220,000 light-years across. That's more than twice the size of our own Milky Way, making Andromeda the largest galaxy in the local group, the collection of galaxies that includes the Milky Way, the Triangulum Galaxy, and around 54 other smaller ones. The size of Andromeda itself is staggering, yet it is just one of the billions of galaxies that make up the vastness of the universe. But size isn't just about how far things stretch. It's about structure, and Andromeda's shape is as grand as its scale. It's a barred spiral galaxy, one of the most common forms in the universe, yet Andromeda's version is anything but ordinary. Its spiral arms extend far into space, each one filled with stars, nebulae, and vast clouds of gas and dust. But it's the galactic core that reveals the true nature of Andromeda's power and complexity. At the center of the galaxy lies a supermassive black hole, just like in the Milky Way. This black hole is millions of times the mass of our sun. It sits quietly at the heart of the galaxy, pulling in stars, gas, and dust. Its gravitational influence is so powerful that it shapes the entire structure of Andromeda. This central bulge, composed of older stars, gives the galaxy its distinct, elliptical core. It's the anchor around which the spiral arms rotate, a cosmic dynamo that drives much of the galaxy's motion and evolution. Surrounding the bulge are the vast, elegant spiral arms, winding outward like the fingers of a cosmic hand. These arms are not static. They are constantly evolving, birthing new stars, and fueling the continued expansion of the galaxy. Within these arms, new stars are born in what are known as stellar nurseries, massive clouds of gas and dust where gravity forces particles together until nuclear fusion ignites, giving birth to new stars. These stars, over time, will help define Andromeda's future, just as older stars in the core define its present. Yet, even as stars form, there's another force at play in Andromeda: gravity. The massive size of the galaxy means that its stars don't just move in predictable circular orbits. Some stars in the outer reaches of Andromeda's spiral arms travel faster than others, pulled inward toward the central bulge. In fact, these stars are caught in an intricate dance, influenced by the gravitational forces not just from the black hole at the center, but from the galaxy's massive halo of dark matter. This halo, composed of dark matter, is one of the great mysteries of Andromeda. Though invisible, dark matter exerts a gravitational pull that helps bind the galaxy together. Without it, the galaxy would simply fly apart. Yet, despite its importance, dark matter remains largely undetectable, a ghostly presence that astronomers can only infer through its gravitational effects on visible matter. And it's this hidden component of Andromeda, this vast, unseen halo, that gives the galaxy its enormous mass. From the oldest stars in the bulge to the youngest stars in the spiral arms, Andromeda's stellar populations tell the story of the galaxy's long and varied history. The older stars in the bulge are red and orange, dimmer than their younger counterparts. They've burned their fuel over billions of years, slowly fading as they age. These stars are the remnants of Andromeda's earliest days, a testament to the galaxy's ancient formation. Meanwhile, the younger stars in the spiral arms are blue and bright, shining fiercely as they burn their fuel at a much faster rate. But Andromeda is more than just stars. It's a galaxy rich with gas and dust, raw materials for new star formation. These interstellar clouds are vast and turbulent, full of chemical elements that are constantly being recycled through the galaxy. The stars form, burn out, explode, and send their material back into the galaxy, where it can form new generations of stars and planets. This process is what makes Andromeda a living galaxy, always in a state of flux, always evolving. Andromeda is not just a singular entity. It is a dynamic, interacting system. For billions of years, it has been absorbing smaller galaxies that have fallen into its gravitational grip. These smaller galaxies, now mere remnants, have been consumed by Andromeda, their stars and gas now part of its massive structure. This process of galactic cannibalism is common in the universe, as larger galaxies like Andromeda and the Milky Way continue to grow by merging with their smaller neighbors. Today, Andromeda's interaction with the Milky Way is one of the most fascinating aspects of its life cycle. The two galaxies are on a collision course, set to collide and merge in about 4 billion years. While the chances of individual stars colliding are slim, because stars are so far apart, the gravitational forces at play will completely reshape both galaxies. The resulting collision will form a new, larger elliptical galaxy. In the process, new stars will be born, and new stellar structures will emerge from the chaos. Even as Andromeda and the Milky Way hurtle toward each other, they are not alone. Andromeda is part of the Local Group, a collection of galaxies bound together by gravity. The Local Group contains more than 50 galaxies, but Andromeda and the Milky Way dominate, both in mass and size. As both galaxies approach each other, they will continue to influence the smaller galaxies in the group, further shaping the evolution of the entire region. Andromeda's massive size and intricate structure make it not just a key object of study, but a window into the future of our own galaxy. By studying Andromeda, we can better understand the life cycle of galaxies, from birth to evolution to eventual merger. We can observe the forces at work within a galaxy, gravity, stellar formation, dark matter, and how they work together to create the dynamic systems that make up the universe. Yet, despite all the information we've gathered, Andromeda remains a mystery in many ways. There is still much we do not know about the galaxy's inner workings, its dark matter distribution, and the exact fate it will face when it collides with the Milky Way. As our technology continues to advance, we will unlock even more of Andromeda's secrets, expanding our understanding of what it means to be a galaxy and what it means to be a part of the universe itself. Focus on Andromeda's spiral arms, central bulge, and supermassive black hole. Among the most striking features of Andromeda's immense structure are its graceful spiral arms. These arms, which spiral outward from the galaxy's dense center, are the very heart of the galaxy's form. Andromeda's spiral pattern is not just a simple curve. It's a dynamic, evolving structure that reflects the ongoing processes of star birth, stellar death, and cosmic evolution. Each of Andromeda's spiral arms is a complex web of stars, gas, dust, and stellar remnants, all bound together by the powerful force of gravity. As the galaxy spins, These arms appear to sweep outward, stretching hundreds of thousands of light-years from the galactic core. These arms aren't uniform. Each is a mix of bright, young stars surrounded by dark lanes of dust and gas. Where stars are born, the arms glow brightly, while darker regions of dust create shadows, giving Andromeda its distinctive, dramatic appearance. These arms are not static. They are dynamic, constantly shifting and evolving. The stars within the spiral arms are born from vast clouds of gas and dust, stellar nurseries where new stars ignite in spectacular fashion. As new stars form, older ones die, often in violent supernova explosions, scattering their material back into the arms, where it may help create the next generation of stars. This ongoing cycle of birth and death is what keeps Andromeda's spiral arms both vibrant and constantly changing. The spiral arms also play a role in the distribution of matter across the galaxy. The density of stars and gas is highest in the spiral arms, but as you move outward from the core, the material becomes less dense. The arms themselves act as cosmic highways, where stars move in and out of clusters, passing by each other in a dance driven by the galaxy's overall gravitational structure. Now, at the very heart of Andromeda lies its central bulge, a dense, massive concentration of stars. This bulge is the galaxy's core, the place where the oldest stars reside. These stars have lived long lives, burning through their fuel and giving off light that has traveled across time and space to reach us. Unlike the stars in the spiral arms, which are young and energetic, the stars in the bulge are older, redder, and dimmer. They have been around for billions of years, long before the first humans looked to the stars. The bulge of Andromeda is not simply a collection of old stars. It's also where the galaxy's supermassive black hole resides. At the center of this bulge lies a black hole that is millions of times the mass of our Sun. This black hole is the engine that powers much of the galaxy's motion. Its gravitational pull is so strong that it affects the motion of stars near the core, pulling them into high-speed orbits around it. The black hole's influence extends far beyond the stars in its immediate vicinity, shaping the entire galaxy's structure. Supermassive black holes, like the one at the center of Andromeda, are still somewhat of a mystery. Scientists know that they are formed through the gradual accumulation of mass over billions of years. As gas and dust fall into the black hole, they are compressed and heated to extreme temperatures, releasing vast amounts of energy. Some of this energy is emitted in the form of radiation, and in some cases, material falling into the black hole is ejected at nearly the speed of light, forming jets of matter that can extend well beyond the galaxy's edge. Despite their immense size and gravitational power, these black holes are not visible in the traditional sense. We cannot directly observe them with the naked eye. Instead, we detect them by observing the behavior of the stars and gas around them. The way stars move in the core of Andromeda suggests the presence of a massive, invisible object pulling them inward. The very fact that Andromeda's spiral arms rotate at the speed they do points to the black hole's influence. It's the unseen gravitational anchor that keeps the galaxy's stars in motion. The size of Andromeda's black hole is remarkable. At millions of times the mass of the Sun, it exerts an influence far beyond what we can easily comprehend. But the black hole doesn't just sit quietly at the galaxy's center. It's actively feeding, pulling in gas, dust, and even stars. This process of accretion fuels the galaxy's growth, but it also creates high-energy phenomena like quasars and active galactic nuclei, which can be detected from vast distances. Though Andromeda's black hole is the most massive object at its center, it is not the only one of its kind. In fact, every major galaxy appears to harbor a supermassive black hole at its core. This suggests that these black holes play an essential role in shaping galaxies, forming, growing, and potentially even dictating their evolution over time. As we learn more about Andromeda's core, we come closer to understanding how these behemoth objects influence the galaxies they inhabit. The spiral arms, central bulge, and supermassive black hole of Andromeda are more than just fascinating features of the galaxy. They are key components of its ongoing story. They reveal the mechanisms by which galaxies form, grow, and change over time. Understanding these features is crucial to understanding the broader processes that govern the universe. And as we continue to explore Andromeda, we will uncover more secrets about how these galactic components interact, how they shape the galaxy's future, and how they may eventually lead to a collision with our own Milky Way. Through modern technology, we are able to peer into Andromeda's deepest corners. Telescopes, both on Earth and in space, continue to reveal more details about its spiral structure, the motion of stars, the behavior of gas clouds, and the power of its central black hole. Each discovery brings us closer to understanding how galaxies like Andromeda evolve, interact, and, in the case of the Milky Way and Andromeda, collide. What we learn from Andromeda today will shape how we understand the future of our own galaxy and, ultimately, our place in the cosmos. Focus on Andromeda star clusters, nebulae, and gas clouds. Beyond the grand structure of Andromeda's spiraling arms and its massive central bulge lies a breathtaking world of stellar birthplaces, clusters, and mysterious clouds of gas. These are the building blocks of the galaxy, where new stars come to life, where cosmic material is recycled, and where the very fabric of the galaxy is shaped. Zoom in with me, and let's explore Andromeda's most stunning features. First, let's look at the star clusters. These dense groups of stars are the heart of Andromeda's vibrant star-forming regions. Some of these clusters are thousands, even millions of stars packed together in an area no larger than a few hundred light-years. They are the cosmic jewels of the galaxy, where the brightest and hottest stars burn in a fierce burst of energy, pushing the galaxy's boundaries. These clusters, many of which have been forming for billions of years, contain stars of various ages. Some are young, blazing with energy, while others are old and dying, their light a faint echo of a long-past brilliance. In these clusters, the stars orbit around each other, locked in a dance of gravity, forming a system where their interactions create new phenomena. Over time, these star clusters evolve, either merging with others or disintegrating as the stars are pulled in different directions. But even as these clusters change, they continue to emit light, their stars serving as a constant reminder of the galaxy's ongoing life cycle. Then there are the nebulae, the colorful clouds of gas and dust that swirl through Andromeda. These nebulae are not just beautiful, they are the birthplaces of stars. When massive clouds of hydrogen gas and dust collapse under their own gravity, they create dense regions where new stars begin to form. The process of star formation is complex and violent, as the gas heats up and ignites, triggering nuclear fusion in the heart of the newly forming star. One of the most remarkable nebulae in Andromeda is the NGC 206, a vast star-forming region in the galaxy's spiral arms. It's a brilliant nebula, glowing with the energy from newly born stars. These young stars emit ultraviolet light that ionizes the surrounding gas, causing it to glow brightly in various colors. This nebula is a cosmic nursery, the birthplace of hundreds of new stars, and it is one of the brightest regions in Andromeda, visible even from Earth's telescopes. Just as important are the darker regions of Andromeda, nebulae filled with gas and dust that seem to obscure the view of distant stars. These clouds don't shine in visible light like the glowing nebulae. Instead, they absorb light, making them appear as dark patches in the galaxy's spiral arms. These dark nebulae are the remnants of star formation, the regions where gas and dust are yet to condense into new stars, or where older stars have expelled material into space. These dark clouds play a crucial role in the life cycle of the galaxy, as they contribute to the ongoing creation of new stars and planets. As we move deeper into the galaxy, we come to the gas clouds that fill Andromeda's arms. These clouds are not as dense as the nebulae, but they are no less important. They act as reservoirs of material, waiting for the right conditions to collapse and form new stars. The gas in Andromeda's arms is primarily hydrogen, the most abundant element in the universe, which serves as the raw fuel for star formation. Over billions of years, the gas clouds in Andromeda have been slowly feeding the galaxy's stellar nurseries, providing the material needed to keep the process of star formation going. These gas clouds are also the site of some of the most spectacular phenomena in the galaxy. When new stars are born, their intense radiation pushes the surrounding gas outward, creating vast cavities in the clouds. These star-forming regions are surrounded by shock waves of gas and dust, which are expelled into space at incredible speeds. The material from these shock waves interacts with surrounding clouds, creating even more stars in a constant cycle of birth, destruction, and rebirth. Andromeda's gas clouds also contribute to the galaxy's ongoing evolution. The gas flows through the spiral arms, giving the galaxy its distinct shape. Some of the gas is pulled inward by gravity, where it will eventually collapse into the galaxy's central regions, feeding the black hole at the heart of Andromeda. This constant cycle of gas flowing in and out of the galaxy's arms and core is a key feature of Andromeda's ongoing transformation. One of the more mysterious features of Andromeda's gas clouds is the way they interact with each other. In some regions, the gas is slowly pushed toward the galaxy's center, drawn in by the gravitational pull of the central bulge and black hole. In other regions, the gas is pushed outward, creating vast streams of material that stretch far beyond the galaxy's outer limits. These interactions are not yet fully understood, but they provide a window into the complex forces at work within Andromeda. The star clusters, nebulae, and gas clouds of Andromeda are not just beautiful to behold. They are the building blocks of the galaxy. They are the sites of creation and destruction, of birth and death. They shape the galaxy's evolution, driving the processes that give Andromeda its distinctive appearance and form. As we study these features, we gain insight not only into the nature of Andromeda but also into the larger processes that govern the universe. And as our telescopes become more powerful and our understanding deepens, we will continue to uncover more secrets hidden within these stunning features. Focus on comparing Andromeda to the Milky Way. Andromeda and the Milky Way, these two galaxies, separated by 2.5 million light-years, are the closest and most significant members of the local group, a collection of galaxies bound together by gravity. But despite their proximity, Andromeda and the Milky Way differ in many ways, from size and structure to how stars form within them. Yet, they are also remarkably similar, sharing common characteristics that make them the most studied galaxies in the universe. Let's start with size. Andromeda is massive, about 220,000 light-years across. That's more than twice the size of our Milky Way, which stretches roughly 100,000 light-years. This gives Andromeda a far more expansive appearance, its spiral arms sprawling over a vast region of space. It contains more stars, more gas, and more dust than the Milky Way, making it the largest galaxy in the local group. But while Andromeda is larger, it is not as dense as the Milky Way. The Milky Way's central bulge is more compact, with stars packed tightly together. In contrast, Andromeda's stars are more spread out, particularly in its outer regions. The Milky Way and Andromeda are both spiral galaxies, but their spirals have distinct differences. The Milky Way has a tighter, more organized spiral, with its arms bending smoothly from the central bulge. Andromeda, on the other hand, has a looser, more expansive spiral structure. Its arms are more spread out and less symmetrical, a result of its larger size and the gravitational interactions it's had with smaller galaxies over billions of years. The shape of Andromeda's spiral arms is also influenced by the presence of a large bar at its core, a feature the Milky Way lacks. And this bar is an interesting feature of Andromeda's structure. The central bulge of Andromeda is a tightly packed region of older stars, and the presence of a bar structure makes the galaxy's inner core even more distinctive. The Milky Way, while it has a bulge at its center, doesn't have the pronounced bar that Andromeda does. This bar plays a crucial role in the dynamics of the galaxy, helping to channel gas from the outer regions toward the center, feeding the central supermassive black hole and supporting the ongoing star formation in the galaxy's arms. When we look at star formation, Andromeda and the Milky Way both exhibit active stellar birth. However, the rate at which stars are forming differs. Andromeda, being slightly older, has fewer new stars forming in the inner regions compared to the Milky Way, but it still has active star-forming regions in its spiral arms. The spiral arms of Andromeda are teeming with young stars, particularly in regions like NGC 206, a star-forming complex in its northern arm. But compared to the Milky Way's more tightly wound arms, Andromeda's arms appear more spread out, and the stellar nurseries are slightly more dispersed. One of the key drivers of star formation in both galaxies is the presence of massive gas clouds. Both Andromeda and the Milky Way are filled with vast clouds of hydrogen, the raw material from which stars are born. But Andromeda has a higher proportion of gas in its outer regions, allowing for greater star formation in the outer spiral arms. The Milky Way, while still hosting significant gas clouds, has a more concentrated region of star formation in its arms, thanks to the higher density of its interstellar medium. Both galaxies also share a supermassive black hole at their cores, but Andromeda's black hole is somewhat more active. At the center of Andromeda sits a black hole that is about 100 million times the mass of our Sun. This black hole plays a critical role in the galaxy's dynamics, particularly in the way stars and gas behave near the center. The Milky Way's black hole, while similar in mass, has a quieter presence. It exerts a powerful gravitational pull, but its activity, in terms of accreting matter, is less intense than Andromeda's. This contrast in black hole activity suggests different histories and processes in the growth of both galaxies. One of the most fascinating differences between Andromeda and the Milky Way is the way these galaxies interact with their satellite galaxies. Andromeda has a larger number of smaller galaxies orbiting it, including M32 and M110, which are dwarfs compared to Andromeda. These galaxies are slowly being pulled in by Andromeda's gravity. The Milky Way also has smaller galaxies in its orbit, like the Large and Small Magellanic Clouds, but it is currently interacting with fewer galaxies than Andromeda. These interactions have shaped Andromeda's structure over billions of years and will continue to influence its future. The Milky Way and Andromeda will eventually collide, but for now, their gravitational influences are somewhat different due to the way their satellite galaxies are distributed. Despite all these differences, Andromeda and the Milky Way are mirror images of one another. They both have spiral structures, both host supermassive black holes, and both contain billions of stars. Both galaxies have undergone similar histories of star formation, galactic collisions, and growth. It's as if Andromeda is a larger, more expansive version of the Milky Way, with similar features and processes occurring on a grander scale. And that collision between the two galaxies is inevitable. In about 4 billion years, Andromeda and the Milky Way will merge, forming a single elliptical galaxy. But even in this merging, both galaxies will retain their unique histories, shaping the future of the new galaxy that will emerge. In the meantime, the two galaxies continue to orbit each other, their stars moving in intricate patterns dictated by gravity. While individual stars may not collide, the effects of their mutual pull will eventually result in a new galactic structure, one that will reflect the best of both galaxies. And as we look at Andromeda, with its size, structure, and star formation, we gain insight into the Milky Way's past, present, and future. Understanding Andromeda's massive form helps us understand our own galaxy's place in the universe and its eventual fate. And as our technology advances and we learn more about Andromeda, we'll continue to uncover the mysteries of this magnificent galaxy, which shares so much in common with our own yet remains distinct in its size, shape, and processes. Presenting images of Andromeda from different telescopes and probes. Across centuries of observation, the face of Andromeda has slowly revealed itself. What was once a distant, hazy smudge in the night sky is now one of the most photographed and studied galaxies in existence. Each image from our telescopes and probes brings us closer to the heart of this colossal galaxy, allowing us to experience its grandeur and uncover its many secrets. Through the Hubble Space Telescope, Andromeda has been captured in breathtaking detail. The Hubble's cameras have produced some of the most iconic images of the galaxy, allowing us to peer deep into its spiral arms, observe its vibrant star clusters, and uncover regions of intense star formation. Hubble's high-resolution images reveal the structure of Andromeda as never before, offering a clear view of its spiral arms, the vast distances between its stars, and the central bulge that houses the supermassive black hole. One of the most stunning images captured by Hubble is the famous Hubble's Deep Field, which shows Andromeda in striking detail. Here, the galaxy is depicted with its bright blue stars glowing vividly in the arms, surrounded by dark patches of dust that make the galaxy look like a cosmic whirlpool. These images show Andromeda's dynamic features, its bright, youthful stars in contrast to the darker, older regions, giving us a sense of the ongoing processes at work within the galaxy. But the view of Andromeda doesn't end with Hubble. The space probe known as the Chandra X-ray Observatory has provided us with a completely different perspective. While Hubble captures the visible light from stars, Chandra looks at the universe through X-rays, allowing us to see the high-energy phenomena taking place in Andromeda's core. Here, we can observe the glowing jets of material being ejected from the supermassive black hole at the center of the galaxy. The X-ray images reveal the unseen forces at work in Andromeda's central region. The immense power of the black hole as it pulls in gas and matter, heating it to millions of degrees before ejecting it as energetic radiation. Moving beyond Hubble and Chandra, the very recently launched James Webb Space Telescope, JWST, has begun to offer unprecedented infrared images of Andromeda. These infrared observations are a game-changer, providing an entirely new perspective on the galaxy. Where Hubble and Chandra show the visible and X-ray emissions, JWST allows us to peer through the dust and gas clouds that typically obscure our view. In its infrared images, we can see the hidden regions where stars are forming, where dark clouds of gas and dust are collapsing to give birth to new generations of stars. JWST's ability to see through Andromeda's dust has revealed previously hidden star-forming regions that were once invisible to even the best optical telescopes. By measuring the infrared light emitted by these stars, we gain a deeper understanding of the chemical composition and temperature of these new star systems. In one image, JWST captured a vast nebula in Andromeda, where young stars are being born, their light ionizing the surrounding gas and causing it to glow with rich hues of red and orange. On the other side of the spectrum, radio telescopes like the Very Large Array VLA have helped map Andromeda's gas clouds. Radio waves can pass through dust and gas clouds that block visible light, providing a unique way of observing the galaxy. The VLA's maps of Andromeda show a detailed picture of how gas moves through the galaxy, how it accumulates in the spiral arms, and how it feeds the ongoing star formation that characterizes much of the galaxy's spiral structure. These radio images also reveal the movements of cosmic material in real time, offering clues about the dynamics and interactions within the galaxy. Each of these telescopes and probes adds a layer of depth to our understanding of Andromeda. By combining their data, astronomers have been able to create a more complete picture of the galaxy, an image not just of its stars and nebulae, but of the complex and ever-changing processes that define its evolution. The collective effort to capture Andromeda's beauty and complexity continues to push the boundaries of our knowledge and our technological capabilities. But beyond the scientific achievement, these images remind us of the sheer grandeur of the universe. Andromeda is more than just a distant object of study. It is a testament to the cosmic processes that govern the life cycle of galaxies. Every image captured, whether from a visible light telescope like Hubble, an X-ray observatory like Chandra, or an infrared marvel like JWST, reveals a galaxy in motion, alive with the energy of new stars, the gravity of its supermassive black hole, and the forces that will continue to shape its future. Through these telescopes and probes, Andromeda is no longer a faint, distant cloud in the sky. It is a vibrant, living galaxy, full of stars, gas, dust, and mystery. Each new image gives us a glimpse into the vast scale of the universe, a reminder that we are part of something far larger and more awe-inspiring than we could have ever imagined. With every observation, we uncover more of the story of Andromeda, one of the most magnificent and mysterious galaxies in our cosmic neighborhood. Chapter 4: The Collision of Giants, Milky Way and Andromeda. The future of Andromeda and the Milky Way. Predicted future collision. In the vast stretch of time and space, the present is but a fleeting moment. Our universe is a dynamic, ever-changing place. While we live in the here and now, events on a galactic scale are unfolding in the far future, where the forces of gravity and time weave their cosmic dance. And one of the most dramatic and inevitable events in the history of the local group, the merger of our Milky Way with the Andromeda Galaxy, is on its way. But this monumental collision won't happen tomorrow. It won't even happen in a century. It is set to unfold in roughly 4 billion years. At that time, the two largest galaxies in our local group will begin their slow but inexorable approach toward each other. Andromeda, which is already on a collision course with the Milky Way, will eventually merge with our galaxy, forming a new, larger elliptical galaxy. This event is so far in the future that it's impossible for us to experience it directly, yet its inevitable nature is written into the very fabric of space itself. We know that this event will reshape not just the structure of our galaxy, but the very nature of the stars, planets, and systems within it. Right now, the Milky Way and Andromeda are separated by about 2.5 million light-years, but the distance between them is closing. Andromeda is moving toward us at about 110 kilometers per second. While this may sound fast, the true impact of the collision will not be felt for billions of years. In fact, the stars themselves won't collide. The vast distances between stars in both galaxies mean that direct star-on-star collisions are exceedingly rare. But the gravitational forces at play will cause massive shifts in the structure of both galaxies. As Andromeda draws closer, its gravitational pull will begin to distort the Milky Way. Our spiral arms, long the defining feature of our galaxy, will be stretched and warped by the immense forces. Gas clouds will be disturbed, triggering new waves of star formation as material is compressed and squeezed into stellar nurseries. But the central cores of both galaxies will be where the most intense action occurs. The supermassive black holes at the center of both galaxies will eventually find themselves on a collision course too. At the point of the merger, these two black holes will spiral toward each other, eventually merging into an even larger supermassive black hole, billions of times the mass of the Sun. The merger of these black holes will release an enormous amount of energy, sending gravitational waves rippling through space. These waves, like ripples in a pond, will travel outward, carrying the echoes of the cosmic collision far beyond the local group. While the merger between the Milky Way and Andromeda will be a breathtaking spectacle, it will also be a time of profound change for the stars, planets, and systems within both galaxies. The collision will disrupt the orbits of countless stars, pushing them into new trajectories. As the galaxies pass through each other, stars will pass by at incredible speeds, affected by the gravitational pull of the other galaxy. Some stars will be ejected from the newly merged galaxy entirely, flung into intergalactic space. Others will be drawn into the newly formed supermassive black hole. Yet, the collision of the Milky Way and Andromeda won't just be about destruction. It will also be a time of creation. The immense energy generated by the merger will trigger new waves of star formation. Gas and dust from both galaxies will be compressed, creating new stellar nurseries. In the wake of the collision, the galaxy will stabilize, its spiral structure giving way to a more spherical, elliptical shape. The stars that survive the cosmic collision will form a new population in a galaxy that is larger, denser, and different from both the Milky Way and Andromeda as we know them. Throughout all of this, the Earth's fate will also be tied to the cosmic dance. By the time the collision occurs, the Sun will have entered its red giant phase, expanding far beyond its current size and potentially consuming the inner planets, including Earth. However, even if the Earth survives the Sun's expansion, it will still be subject to the gravitational chaos of the galactic merger. The solar system's position within the Milky Way will shift dramatically, and the Sun may even be flung into a new orbit around the newly formed galaxy's center. Life, as we know it, may not exist in such a future, but the Sun's expansion, combined with the massive galactic shift, would ensure that any remnants of the Earth's habitability will be gone long before the collision itself. However, if we were to observe this event from a vantage point far away, perhaps from another galaxy, the collision of the Milky Way and Andromeda would appear as a cosmic ballet, a slow-motion dance of light, dust, and stars. The beauty of this event is in its scale, the sheer magnitude of the forces at play, and the fact that galaxies, like stars, have lifespans that span billions of years. This merger represents the natural progression of galactic evolution, a chapter in the life cycle of two of the most significant galaxies in our corner of the universe. Despite the cataclysmic nature of this event, the merger between Andromeda and the Milky Way is not the end. It is, in fact, the beginning of a new galaxy, a galaxy that will continue to evolve for billions of years after the collision, possibly giving birth to new stars and systems that may one day support life in distant corners of the universe. Despite the cataclysmic nature of this event, the merger between Andromeda and the Milky Way is not the end. It is, in fact, the beginning of a new galaxy. A galaxy that will continue to evolve for billions of years after the collision, possibly giving birth to new stars and systems that may one day support life in distant corners of the universe. Just as we look at Andromeda and the Milky Way today and see two galaxies in motion, so too will future generations look back at this moment in cosmic history and see it as the beginning of something far greater, an event that will reshape not just the galaxies themselves, but our understanding of the universe. And while we may never witness this grand collision firsthand, it remains one of the most profound and awe-inspiring events in the timeline of the cosmos, presenting the merging of the two galaxies into an elliptical galaxy. The collision of the Milky Way and Andromeda is an event that stretches beyond the realm of human experience. For billion years from now, the two galaxies will draw closer, their immense gravitational forces starting a slow but irreversible journey toward merger. As Andromeda and the Milky Way spiral toward each other, they will begin to interact, triggering a cascade of events that will reshape both galaxies into something new. The collision, though incredibly far off, is a process written into the laws of physics, a cosmic inevitability. As the galaxies move closer, their spiral shapes will begin to warp. Andromeda's arms, vast and sweeping, will be stretched and pulled by the gravitational forces of the Milky Way, while our galaxy's arms will be distorted by Andromeda's massive size. These gravitational interactions will trigger star formation in unexpected places, compressing gas and dust clouds and igniting the birth of new stars. At the same time, gas will be funneled toward the centers of both galaxies, feeding their supermassive black holes. These black holes, already massive in their own right, will become even more powerful as they consume the gas and debris swirling around them. As the two galaxies pass through each other, their stars, vastly separated by the immense distances between them, will largely avoid direct collisions. Instead, the galaxies will interact in a way that will alter the paths of individual stars. Some will be ejected from the galaxies entirely, flung into intergalactic space by the powerful gravitational forces. Others will be caught in the gravitational tug-of-war between the two galaxies, thrown into new orbits around the newly merged center. During the early stages of this merger, the Milky Way and Andromeda will pass through each other like two clouds of gas. The gravitational forces at play will stretch and elongate the galaxies. The initial interactions between the two galaxies will lead to dramatic shifts in their spiral arms, and the black holes at their centers will begin their slow dance toward each other. As the two supermassive black holes draw closer, they will spiral inward, losing energy with each orbit. The closer they get, the faster they move until, eventually, they collide and merge into a single, far more powerful black hole. This collision between the two galaxies, though it will create chaos, will also birth a new galaxy. The merger will begin to blur the lines between the two distinct galaxies, reshaping them into a new elliptical galaxy. The vast spiral arms of both galaxies will be lost, and the dense, tightly packed stars that make up an elliptical galaxy will replace them. The end result will be a galaxy that is much larger, rounder, and more massive than either the Milky Way or Andromeda could have ever been on their own. However, even though the collision is certain, the timeline is spread out across billions of years. During this lengthy process, stars will continue to be born and die. Some will survive the chaos, while others will be ejected from the galaxy altogether. Planets, including Earth, may or may not still exist by the time the merger is complete, but the ultimate fate of these systems will be determined by the forces at play. The gravitational disturbances could send our solar system into a new orbit or potentially fling it into the outer reaches of the newly formed galaxy. These changes will be so gradual that no single star or solar system will notice them on a human timescale. In fact, the stars themselves will continue their orbits, only slightly altered by the pull of the galaxy's gravity. But when viewed over billions of years, the result is a complete transformation of both galaxies, their collision giving birth to a new, massive elliptical galaxy. During the final stages of the merger, both galaxies will have lost much of their distinct identity. The merger will leave behind a galaxy that is more compact, with a smoother elliptical shape. The central supermassive black hole will become the centerpiece of this new galaxy, its powerful gravitational influence affecting the orbits of the stars that remain. New stars will continue to form in the remaining gas clouds, and the outer regions of the galaxy will eventually stabilize into a smooth, almost featureless expanse. By the time the merger is complete, the new galaxy will be a behemoth, a cosmic giant made from the best qualities of both the Milky Way and Andromeda. It will be a place where the stars and planets that remain have been reshaped and reorganized by the forces of gravity. This new elliptical galaxy will be a living, breathing system, continuing the cycle of star birth and death for billions of years to come. But even as the galaxies collide and merge, their histories will continue to resonate throughout the universe. The stars that are born from this collision will carry the legacy of both Andromeda and the Milky Way, as will the planetary systems that emerge from the galactic dust. The merger will be the final chapter in the story of these two great galaxies, and from the ashes of their collision, a new galaxy will rise, destined to continue its journey through the cosmos. The inevitable future collision between the Milky Way and Andromeda is not an end, but a transformation. It is the next step in the evolution of our universe, a cosmic dance that will continue to shape the galaxies and stars that we see today. As we study these galaxies, we gain insight not just into their past, but into our own future, one that will be marked by the ongoing cycle of creation, destruction, and rebirth. Breaking down the science of galaxy collisions. The idea of galaxies colliding sounds like a cataclysmic event, one that conjures images of fiery explosions and stars crashing into one another. But in reality, the process of galactic collisions is much more complex and far less dramatic than we might first imagine. At a cosmic scale, while these events cause vast changes, they are also guided by fundamental forces, gravity and dark matter, that determine the fate of both galaxies and the stars within them. At the heart of every galaxy is gravity. It is the force that governs the motion of stars, gas, and even entire galaxies. When two galaxies approach each other, the force of gravity pulls them together. But despite the massive size and mass of these galaxies, the stars themselves are spread out across enormous distances. For example, the stars in both the Milky Way and Andromeda are separated by vast distances, often millions of kilometers. The average distance between stars is so large that, even in a head-on collision, it is incredibly unlikely that any two stars will ever collide. Instead, as Andromeda and the Milky Way draw closer, gravity causes the stars to be deflected from their original paths. The gravitational forces act like a cosmic tug-of-war, pulling stars and gas clouds toward each other, while also sending them flying outwards, changing their orbits. This is why, despite the collision, stars in both galaxies will largely avoid each other. They won't crash into one another, but they will be affected by the gravitational pull of the other galaxy, altering their paths. However, while the stars themselves may not collide, the gas and dust within the galaxies are a different story. These regions are much denser, and when galaxies collide, their gas clouds will interact more directly. As the two galaxies collide, their gas clouds will compress, leading to massive bursts of new star formation. This process is called starburst activity, and it occurs when gas is compressed to such an extent that it triggers the formation of new stars. These star-forming regions will be some of the brightest and most energetic places in the newly merging galaxy. Beyond gravity, there is another invisible force at work during galaxy collisions: dark matter. This mysterious substance makes up a significant portion of a galaxy's mass, yet it doesn't emit light or radiation. We can't see dark matter directly, but we can measure its effects by observing how galaxies move and how their gravitational influence bends the path of light. Dark matter does not interact with normal matter like gas or stars in the same way, but it has a profound effect on the overall dynamics of a galaxy. When two galaxies collide, dark matter plays a crucial role in shaping the outcome. As both Andromeda and the Milky Way merge, their dark matter halos will collide and merge as well. This dark matter will guide the gravitational interactions between the two galaxies, influencing the path of stars and gas. In fact, the dark matter halos of the two galaxies will become interwoven, affecting the overall shape and motion of the new, merged galaxy. It is this unseen influence that will help determine the final structure of the resulting galaxy. Over the course of the collision, gravity will pull both galaxies closer and closer together. And as they merge, the supermassive black holes at their cores will also begin to interact. These black holes, which are already massive and powerful, will eventually spiral toward each other, drawn together by their mutual gravity. As they approach, they will release enormous amounts of energy in the form of gravitational waves, ripples in the fabric of space-time itself. The merging black holes will eventually collide, forming an even larger supermassive black hole at the center of the new galaxy. The collision will release an enormous burst of energy, and the resulting gravitational waves will ripple across the universe, detectable by future gravitational wave observatories. This dramatic event will mark the final stage of the merger, leading to the formation of a new, massive elliptical galaxy. While the galaxies themselves will undergo radical changes during the collision, their stars will experience a more subtle transformation. Most stars will simply be deflected by the gravitational forces at play, and while their orbits will change, they won't collide. However, some stars will be ejected from the galaxies altogether, flung into the void of intergalactic space. These stars will become rogue stars, no longer bound to any galaxy. Their journeys through space will be long and solitary, and their fate will be to wander alone through the cosmos. As the galaxies continue their dance, the process of merging will take billions of years. The stars will settle into new orbits, and the gas clouds will eventually form new stars in the center of the new galaxy. Over time, the once distinct spiral shapes of Andromeda and the Milky Way will give way to a smooth, rounded elliptical galaxy full of stars, gas, and dark matter. The collision will have completely altered the shape and structure of both galaxies, and the resulting elliptical galaxy will be a giant, containing billions of stars and an enormous supermassive black hole at its core. Though the collision itself may seem chaotic, it is, in fact, a natural part of the life cycle of galaxies. Collisions and mergers between galaxies have occurred throughout the universe's history, shaping the galaxies we see today. And while the merger of the Milky Way and Andromeda will be a dramatic event, it is just one chapter in the ongoing story of the universe's evolution. Potential impacts of the collision on star systems and planets. As Andromeda and the Milky Way draw closer, their collision will not just alter the shape of the galaxies themselves, but will send shockwaves across the star systems and planets within them. The gravitational forces at play during this galactic collision are so immense that they will affect every object within both galaxies, from the tiniest asteroids to the largest star systems. And while stars will largely avoid direct collisions due to the vast distances between them, the consequences for star systems, including their planets, will be profound. During the early stages of the collision, the orbits of stars will begin to shift. The gravitational pull between the two galaxies will gradually alter the paths of stars as they pass close to one another. For stars near the centers of both galaxies, the effects will be dramatic. As Andromeda and the Milky Way begin to interact, stars will be drawn toward each other, their paths distorted by the powerful gravitational forces. These stars may be flung into new orbits, some possibly being ejected entirely from both galaxies and cast into intergalactic space. These rogue stars will no longer be bound by the gravity of either galaxy, wandering alone through the vast emptiness between galaxies. Closer to the galactic centers, the situation becomes even more intense. As the central supermassive black holes of both galaxies draw nearer to each other, their gravitational influence will become stronger, pulling stars and gas with increasing force. The stars in these regions will experience the most dramatic changes. Their orbits will become highly elliptical, stretching out and then plunging back toward the galaxy's core. Some stars may even spiral toward the black holes themselves, falling into the depths where they will be consumed, adding to the black hole's immense mass. For planets, the effects of the collision will be just as catastrophic. As stars move into new orbits, any planets orbiting those stars will likely be sent on a wild ride. Planets that were once in stable orbits around their parent stars may be sent careening through space, caught in the gravitational tug-of-war between the two merging galaxies. Planets that are lucky enough to remain in orbit around their stars will still experience a dramatic shift in their environment as their stars are pulled and stretched by the galaxy's merging forces. In some cases, planets may be ejected from their star systems altogether. In the chaos of this cosmic collision, gravitational interactions between stars, gas clouds, and dark matter may send planets flying into intergalactic space. These rogue planets, like the rogue stars, would drift alone through the vast emptiness, no longer tethered to any star, no longer part of any solar system. Their fate would be bleak, cold, dark, and isolated. But even those planets that remain bound to their stars may not be safe. As the galaxies merge and stars are pushed toward new orbits, the newly formed elliptical galaxy could experience new bursts of star formation in the densest regions. This could create stellar systems full of new stars, and these stars could have planets of their own, possibly habitable, possibly full of life. However, the most violent effects of the collision, such as gravitational radiation and the activity around supermassive black holes, could make any surrounding planetary systems inhospitable. The intense radiation and energy released during the black hole merger could strip away any atmosphere from planets within range, rendering them uninhabitable. Even if a planet survives the chaos and remains in orbit around a stable star, it's likely that the solar system as a whole will change. The planet's star could be sent into a new orbit within the elliptical galaxy, possibly moving closer to the galaxy's center, exposing the planets to intense radiation from new nearby stars. The entire solar system could be transformed, with new cosmic threats looming as it moves through a galaxy filled with unfamiliar dangers. While the Milky Way and Andromeda will ultimately form a new, massive elliptical galaxy, the process leading to this final form will wreak havoc on the star systems and planets within both galaxies. Star systems that survive will emerge in completely new configurations, with stars and planets reshaped by the forces at work during the collision. However, many star systems will be destroyed, and countless planets will be ejected from their orbits, cast into the void of space. But there's a strange beauty in this process. The birth of new stars, the destruction of old systems, the formation of new planetary systems. This is the natural cycle of galactic evolution. Every collision and merger, though violent and destructive, also gives birth to something new. New stars will form from the gas clouds compressed by the collision. New planets will emerge from the stellar nurseries created by the gravitational forces at play. And while life as we know it might not survive in the immediate aftermath of this cosmic event, the collision will set the stage for a new chapter in the history of the universe. Beyond the physical chaos, the Milky Way and Andromeda's collision will provide valuable lessons about the future of galaxies, stars, and planets. Scientists, far in the future, will study the remnants of this event to understand the long-term effects of galaxy mergers. They'll learn how galaxies evolve, how stars interact, and how planetary systems change when galaxies collide. The remnants of the stars and planets affected by the collision will provide a record of the forces at play, a story that will continue to be written in the very structure of the new elliptical galaxy that emerges. Though the collision of the Milky Way and Andromeda will mark the end of one era for these galaxies, it will also signal the birth of a new one. A new galaxy will rise from the ashes, carrying the combined legacy of both galaxies into the future. It will be a galaxy of stars, gas, and dust, one that has been shaped by billions of years of cosmic evolution. And in that galaxy, new planets and new possibilities will emerge, continuing the endless cycle of creation, destruction, and rebirth that defines the universe. The possibility of Earth becoming uninhabitable. As Andromeda and the Milky Way continue their inevitable journey toward merger, one question stands out. What will become of Earth? Our planet, nestled in the relative calm of the Milky Way's outer spiral arm, has witnessed billions of years of life and cosmic history. But by the time this grand collision occurs, for billion years from now, Earth's fate may already be sealed. The collision itself will undoubtedly have its effects, but there are other cosmic forces at play that could render Earth uninhabitable long before the galaxies merge. To understand why, we need to look at a force far closer to home: the Sun. Right now, the Sun is in the middle of its life cycle, a stable star providing the energy that sustains life on Earth. But like all stars, it is not static. Over the next billion years, the sun will slowly burn through its hydrogen fuel, becoming hotter and brighter. As the sun ages, it will begin to expand. The gradual increase in its brightness will have significant consequences for Earth's environment. As the sun becomes hotter, it will emit more radiation, raising the temperature on Earth. In about 1 billion years, the Earth's surface will begin to warm. This will cause the oceans to evaporate, creating a runaway greenhouse effect similar to what we see on Venus. As the temperatures continue to rise, the atmosphere will be. Oceans will boil away, and the atmosphere will lose its oxygen content. Earth will be transformed into a barren, lifeless world, long before Andromeda and the Milky Way even begin to merge. By the time the collision between our galaxy and Andromeda is nearing, the sun will have entered its red giant phase. This phase marks the end of the sun's life as it expands outward, possibly engulfing the inner planets, including Earth. As the sun swells, its outer layers will stretch out and engulf the Earth, causing its surface to melt. Even if Earth somehow avoids direct contact with the sun, the heat from the expanding star will strip away whatever remains of the planet's atmosphere, rendering the Earth completely inhospitable. At this point, even the cosmic collision between Andromeda and the Milky Way will be a secondary concern. Earth will have long been stripped of the conditions that sustain life. However, it's not just the sun's inevitable transformation that will affect Earth's habitability. The cosmic environment around us will continue to change as well, further diminishing the chances for life as we know it. As the Milky Way and Andromeda draw closer to each other, the gravitational forces between the two galaxies will become more intense. These forces will reshape the orbits of stars, including our own Sunday. As the galaxies begin to merge, the sun's position within the galaxy could shift, possibly drawing the solar system closer to the galaxy's center, where gravitational interactions could destabilize the orbits of planets. Such a shift could send the Earth careening into an unstable path, further destabilizing its orbit and pushing it into a zone where life cannot survive. At the same time, the collision of the two galaxies will increase the frequency of cosmic events, such as supernovae and gamma-ray bursts. These explosions, though incredibly far away, will release powerful bursts of radiation capable of reaching the solar system. If Earth's orbit aligns with these energetic events, the planet could be bombarded with lethal radiation, further stripping away its atmosphere and making the surface even less habitable. Another potential factor that could contribute to Earth's inhospitability is the effect of dark matter. While dark matter does not interact with regular matter in the way that light or gravity does, its influence on the structure of galaxies and their interactions is undeniable. During the merger of the Milky Way and Andromeda, the dark matter halos surrounding both galaxies will collide and intermix, reshaping the distribution of mass and gravitational forces. This could result in a change in the dynamics of the solar system, leading to instability in Earth's orbit. A shift in the solar system's orbit could result in Earth moving too close to the sun or too far away, throwing it out of the habitable zone. The combination of the sun's increasing brightness, the disruption caused by the galaxy's collision, and the potential impact of cosmic events and dark matter interactions suggests that Earth's future as a habitable planet is highly uncertain. Long before the two galaxies finally merge into a new elliptical galaxy, Earth may already be a lifeless rock, unrecognizable from the vibrant world we know today. Yet, despite these challenges, Earth's story isn't over yet. While the future collision of galaxies may render Earth uninhabitable, the transformation of the Milky Way and Andromeda represents an opportunity for the universe to evolve. New stars, planets, and even galaxies will emerge from the merger, creating new homes for future life, if life can find a way to adapt to the changing conditions of the universe. In the grand scheme of things, Earth's demise, brought about by the inevitable changes in the Sun and the galactic collision, is simply another chapter in the ongoing story of the cosmos. As galaxies collide and evolve, stars are born, and life is given the chance to take root in new environments. Our planet's fate is written in the stars, but it is not the end of the universe's story. The collision between the Milky Way and Andromeda will mark the beginning of a new era. A new galaxy formed from the ashes of the old, with possibilities yet to be discovered in the far-off future. Chapter 5: The Challenge of Reaching Andromeda. The concept of intergalactic travel. Technological limitations of space travel. Space is vast, stretching out beyond what the human eye can truly comprehend. While our current technology has allowed us to explore the inner reaches of our solar system, venturing beyond that, toward distant stars and galaxies, is still beyond our grasp. The Andromeda Galaxy, located 2.5 million light-years from Earth, is a prime example of how immense the cosmos really is. Though it is our closest neighboring galaxy, the sheer distance between us presents one of the most formidable challenges for space travel. Let's put this distance into perspective. A single light-year, the distance light travels in 1 year, is about 9.46 trillion kilometers. To reach Andromeda at the speed of the fastest spacecraft we've built so far, it would take millions of years. The current record for human-made objects is held by the Parker Solar Probe, which, traveling at a velocity of about 700,000 kilometers per hour, would take nearly 20,000 years just to reach the nearest star, Proxima Centauri, let alone a galaxy 2.5 million light-years away. Even the speed of light itself, which is the fastest possible speed in the universe, is far from fast enough when applied to such massive distances. Light takes 2.5 million years to travel from Andromeda to us, and this speed, although the fastest in the cosmos, is still insufficient to bridge the gap for human exploration in any reasonable amount of time. To get an idea of how this works, consider that the fastest spacecraft in operation today, like the Voyager probes, have been traveling for over 40 years and have only just reached the outer boundaries of our solar system, still far, far short of any intergalactic journey. But speed isn't the only limiting factor in space travel. There's also the issue of fuel. To reach Andromeda, a spacecraft would need an astronomical amount of energy to propel it over such an enormous distance. Current propulsion systems, whether chemical rockets, ion engines, or even the more advanced theoretical propulsion methods, are simply not capable of providing the necessary thrust over the vast expanse of space. The chemical propulsion systems we use today are efficient for short trips, like sending satellites or rovers to nearby planets, but they are far too weak to carry a spacecraft the entire distance to another galaxy. Looking at potential future propulsion technologies, we encounter even greater challenges. Concepts like nuclear fusion or antimatter propulsion, which promise to revolutionize space travel, still remain largely theoretical. While they hold tremendous promise for efficiency and speed, they are not yet viable for practical use. The development of these technologies could take decades or even centuries. Until we make significant breakthroughs in these areas, our journey to other galaxies remains firmly out of reach. One more technological barrier to space travel is the issue of time dilation. This phenomenon arises from the theory of relativity and means that the faster you travel, the slower time moves for you, relative to people on Earth. If a spacecraft were to travel close to the speed of light, the astronauts on board would experience time at a much slower rate than people on Earth. So, while a journey to Andromeda might take millions of years from an Earth-based perspective, the travelers themselves would experience far less time. However, this still creates another challenge: the effects of aging, human health, and the generational aspects of long-term space travel. It's one thing for a spacecraft to travel for centuries or millennia, but another entirely for the people on board to survive such a journey. Furthermore, there is the problem of radiation in deep space. As we travel further from Earth, we move into regions of space that are filled with cosmic radiation, high-energy particles that can damage both spacecraft and humans. In our solar system, we are protected by the magnetic field of the Earth and the Sun, but outside this protective bubble, radiation becomes a serious issue. Even at relatively short distances within our own solar system, astronauts face significant radiation risks. For a mission to Andromeda, the spacecraft would need to shield its crew from these cosmic rays, and doing so would require an enormous amount of energy, mass, and sophisticated technology that we do not yet have. The combination of these technological limitations, vast distances, the speed of our current spacecraft, fuel requirements, time dilation, and cosmic radiation, makes intergalactic travel a monumental challenge. While the dream of reaching Andromeda one day may inspire future generations, we are still far from possessing the tools and technologies required to make this journey a reality. And yet, even as we confront these limitations, the dream of intergalactic travel persists. Each scientific breakthrough brings us closer to the possibility of traveling through space faster, more efficiently, and with greater protection against the hazards that lie ahead. The question remains, can we overcome these immense challenges? What might the next century or two bring in terms of technological advancements? Perhaps the next great leap in space travel will be sparked by new propulsion systems, new materials, or even discoveries we have yet to imagine. Until then, Andromeda remains beyond our reach, distant, mysterious, and waiting. For now, we can only study it from afar, using the most advanced telescopes and space observatories to capture its beauty and complexity. But the journey to Andromeda is not just a technological question. It's also a question of human ambition, imagination, and our relentless desire to push the boundaries of what's possible. Near-light speed travel and time dilation. As we look to the stars, the idea of traveling to distant galaxies like Andromeda seems like an impossible dream. But what if we could travel faster? What if we could approach the speed of light? The concept of near-light speed travel is not just a science fiction fantasy. It's a real, theoretical possibility. However, with it comes a mind-boggling consequence: time dilation. This phenomenon, rooted in Einstein's theory of relativity, would make traveling to Andromeda far more complicated than simply speeding through space. At the heart of this idea is the fact that, according to relativity, as you travel faster and faster, especially as you approach the speed of light, time for the traveler begins to slow down relative to those left behind. This means that, from the perspective of a traveler moving near the speed of light, a journey that might take only a few years could stretch to millennia on Earth. If you were to set out for Andromeda at near-light speed, the experience of time for you would be drastically different from the passage of time for people still on Earth. To grasp this, consider a journey to Andromeda. The galaxy is 2.5 million light-years away. If you were able to travel at 99.9% of the speed of light, the trip could take only a few years for you. But because of time dilation, while those aboard the spacecraft would experience just a few years of travel time, those left on Earth would see 2.5 million years pass by. This effect isn't a trick of perception. It's a fundamental aspect of how time works at high velocities. This phenomenon of time dilation means that if humans were ever able to travel near the speed of light, the world they returned to would have changed drastically. Those who left Earth would find themselves in a future far beyond their comprehension. Generations would pass on Earth, and their descendants might no longer be around to greet them when they return. The traveler, however, would have aged only a few years or decades, despite being gone for millions of years in Earth time. Such a journey would also challenge the very nature of our experience of time itself. The faster you go, the more pronounced the effect of time dilation becomes. At light speed, time for the traveler would stop entirely. Of course, we're nowhere near the capability of reaching such speeds, but as our technology advances, near-light speed travel could one day become a reality. However, the human mind and body would be forced to adapt to this new perception of time. It's not just about moving faster through space. It's about fundamentally altering how we experience the passage of time. At near-light speeds, the traveler's journey would unfold differently from any trip we've ever known. Time would stretch and contract, and the aging process would slow down for the traveler, but this would come at a high cost. Even with the incredible advances required for near-light speed travel, we still don't fully understand how the human body would react to such prolonged periods of time distortion. Would we be able to survive long trips without aging in the same way as those left behind? The biological and psychological implications are still uncertain. In practical terms, reaching near-light speeds would require an immense amount of energy, far more than we can currently generate. The challenge is not just about overcoming the distance, but also about harnessing the energy needed to accelerate a spacecraft to such velocities. Even theoretical propulsion systems like nuclear fusion or antimatter engines face unimaginable engineering hurdles. Yet, the idea of near-light speed travel is still within the realm of possibility. One of the fundamental reasons near-light speed travel is so attractive is its potential to make distant travel in space more accessible. If a spacecraft could travel at such speeds, the vast distances between the stars and galaxies would seem less intimidating. A journey to Andromeda, which would normally take millions of years, could be reduced to a mere fraction of that time. But this leads us to a paradox. How can we venture to distant stars if the very fabric of time changes for the traveler? Not only would we be racing against the clock of the universe, but we'd also be forced to rethink our fundamental concepts of space, time, and what it means to travel. With time dilation, we find ourselves facing a new kind of challenge. While technology may get us there faster, the very nature of time means that we'd be leaving our home and its future behind. The long journey across the stars would not just be a physical voyage. It would also be a journey through a future that would be drastically different by the time we return. Near light-speed travel brings us to the edge of possibility. It forces us to confront the limits of our understanding and the fragility of human existence. The very concept of what it means to travel will be challenged. Time itself will no longer be linear. Instead, it will bend and stretch, and we will have to adapt to a future where the past and present no longer align as we expect. While the dream of reaching Andromeda and other distant galaxies seems out of reach, near light-speed travel offers us a glimpse into the future. It opens the door to a new era of exploration, one where the fundamental rules of the universe may no longer apply in the way we understand them. As we continue to push the boundaries of technology, the journey to the stars may one day be possible, but the nature of time itself will change with it. Theoretical possibilities, wormholes, and stargates. As we grapple with the challenges of traveling to distant galaxies, one question persists. Is there any way to bypass the impossible distances of space, to skip past the vast voids that separate us from other galaxies? This question has inspired scientists and dreamers alike for centuries, leading to some of the most thrilling theories in modern physics. Among them, the concepts of wormholes and stargates stand out as potential shortcuts through space and time, bridging the gaps between galaxies and making intergalactic travel a reality. Wormholes, in their simplest form, are hypothetical passages through space-time that could create shortcuts between distant points in the universe. If they exist, a wormhole would act like a tunnel with two ends, each located at separate points in space-time. Think of it as folding a piece of paper so that two distant points touch, and a hole appears between them. Traveling through this hole could, in theory, allow a spacecraft to bypass the long journey between galaxies, potentially reaching Andromeda in a fraction of the time it would take using conventional methods. These concepts aren't just a product of science fiction. Theoretical physicists like Albert Einstein and Nathan Rosen first proposed the idea of wormholes in the 1930s. Their theory, called the Einstein-Rosen bridge, suggested that wormholes could be possible if certain conditions were met. But despite decades of research, the creation or discovery of a stable wormhole remains a tantalizing possibility rather than a practical reality. So, how could a wormhole form, and what would it take to use one for space travel? One way a wormhole could potentially exist is through the presence of exotic matter, a hypothetical type of matter that has negative energy. This negative energy would counteract the immense gravitational forces that would otherwise collapse a wormhole, allowing it to remain open. Without this exotic matter, any wormhole would collapse before anything could travel through it. Even if exotic matter could be created, maintaining a stable wormhole large enough for a spacecraft to pass through is another monumental challenge. Theoretical models suggest that creating or stabilizing a wormhole could require energy scales far beyond anything humanity is currently capable of generating. This doesn't even account for the immense risks that might accompany such a journey, including the potential for unpredictable distortions in space-time or the consequences of being trapped within the wormhole. Yet, despite these challenges, the idea of wormholes continues to captivate the imagination of scientists and engineers. If they can be created and stabilized, wormholes might offer a solution to the fundamental limitations of space travel. But for now, this remains a theoretical concept, one that would require breakthroughs in physics and technology to even begin to explore. Another related idea is the concept of stargates, often portrayed in popular culture as portals that connect different points in space instantaneously. While the term Stargate is commonly associated with science fiction, it is, at its core, a concept grounded in real scientific principles. Much like wormholes, stargates would allow for the instantaneous travel between distant locations, bypassing the need for ships to travel through space. In some ways, stargates are a natural extension of the wormhole theory, but with a key difference. the existence of a stargate might not require one to physically travel through the wormhole. Instead, a stargate could function as a point-to-point connection where two distant places are instantaneously linked. This concept, although still in the realm of speculation, raises fascinating possibilities about how we might one day travel across the cosmos. Stargates and wormholes are certainly intriguing ideas, but they also raise several important questions. What exactly would happen to an object or person that travels through such a structure? Could we maintain communication across such vast distances? And if wormholes or stargates do exist, where are they? Can we find a natural wormhole in space or wow? And finally, if such pathways through spacetime are possible, why haven't we detected them already? One possibility is that wormholes or stargates could be incredibly rare, or that they could exist at scales far beyond our current ability to detect or access. It's also possible that they are not stable over long periods of time, or that they require conditions we are not yet capable of creating. However, if they do exist, they could offer humanity a way to travel across the cosmos far faster than any conventional means of propulsion could ever achieve. The search for wormholes and stargates is still in its infancy, but it is one of the most exciting areas of scientific research. Theoretical physicists continue to study the equations and models that describe spacetime, seeking ways to open doors to distant galaxies without the need for thousands of years of travel. What we do know is that, even if wormholes and stargates are currently beyond our reach, they represent the kind of thinking that could one day change the course of space exploration forever. Of course, the practical aspects of utilizing a wormhole or stargate are still riddled with questions and challenges. How would we safely navigate through one? What kind of spacecraft would be needed to withstand the immense stresses of such a journey? And what happens if something goes wrong? If we're sent to the wrong location or trapped in a collapsing wormhole? Though the road to practical intergalactic travel remains long, wormholes and stargates represent a bold vision for the future. The idea that we could one day open a door to another galaxy, crossing the vast expanse of space almost instantaneously, remains one of the most tantalizing possibilities for space exploration. Scientific declarations on propulsion technology and obstacles in intergalactic travel. As humanity stands on the edge of a new era in space exploration, one question looms large. How will we travel the immense distances between the stars? To reach galaxies like Andromeda, we need more than just better rockets. We need breakthroughs in propulsion technology, which is the backbone of any space mission. Right now, our technology is limited, but scientists around the world are relentlessly working to change that. To truly understand the barriers we face and what the future holds, let's hear directly from the experts themselves, the scientists and engineers working on the cutting edge of propulsion systems. This is the first. Today, our fastest spacecraft are powered by chemical rockets, which burn fuel to generate thrust. While these rockets have been invaluable in our exploration of the solar system, they are simply not capable of intergalactic travel. The speed at which chemical rockets work is far too slow for us to reach even the nearest stars, let alone another galaxy. To give you a sense of the problem, the fastest spacecraft ever launched, the Parker Solar Probe, travels at speeds of up to 700,000 kilometers per hour. At that rate, it would take around 20,000 years just to reach the nearest star system, Proxima Centauri. Now, imagine trying to cover the 2.5 million light-years to Andromeda. Clearly, we need something far more efficient. Chemical rockets have brought us to the edges of our solar system, but they're inadequate for traveling the vast distances between galaxies. So, scientists are looking for radically new propulsion technologies that could propel us across space at a fraction of the time. Here's another one. When we talk about intergalactic travel, one of the most promising areas of research is ion propulsion. This technology uses electric fields to accelerate charged particles, like ions, to extremely high speeds. Compared to chemical rockets, ion engines are far more efficient, using less fuel while providing a continuous, steady thrust. The NASA Dawn spacecraft, which used ion propulsion to explore asteroids, is a great example of how this technology can work in space. However, while ion propulsion is much more efficient than chemical propulsion, it's still too slow for intergalactic travel. The maximum speed we can currently achieve with ion engines is still a tiny fraction of the speed of light. Ion propulsion represents a leap forward from conventional rockets, but it's still a long way from the speeds needed for traveling to distant galaxies. To truly unlock the potential for intergalactic exploration, scientists are turning to even more advanced ideas. We have the third scientific declaration for you, and it says that one of the most exciting concepts we're exploring right now is nuclear propulsion. The idea behind nuclear propulsion is to use nuclear reactions to generate far more energy than chemical rockets can. Theoretically, this could allow us to reach much higher speeds. There are several concepts within nuclear propulsion, nuclear thermal rockets, and nuclear electric propulsion, for instance. Both harness the immense power of nuclear reactions to provide thrust. Nuclear thermal rockets would heat a propellant using nuclear reactions, while nuclear electric propulsion would generate electricity to power an ion engine. The idea is to create much more power with far less fuel, and the speeds we could achieve with such systems would dramatically shorten the time it takes to reach distant stars. Nuclear propulsion could take us farther and faster than current technologies allow, but the challenges of harnessing nuclear energy in space are immense. There's also the issue of safety, both in terms of the technology itself and the potential for long-term radiation exposure. But nuclear propulsion isn't the only idea on the table. There are more radical, theoretical technologies that could provide even more dramatic advancements. This is the next one. We're also investigating antimatter propulsion, one of the most exciting and promising fields of research. Antimatter, the opposite of regular matter, has the potential to release immense amounts of energy. In theory, a spacecraft powered by antimatter could achieve close to the speed of light, vastly reducing travel time across the galaxy. But we're still a long way from being able to produce enough antimatter to power even a small spacecraft. The current technology for creating and storing antimatter is in its infancy, and we face enormous technical challenges in this area. The amount of antimatter needed for a meaningful spacecraft propulsion system is still orders of magnitude beyond our current capabilities. Antimatter propulsion, though intriguing, is one of the most complex and speculative ideas in the world of space travel. The practical obstacles are enormous, but the potential benefits, speeding us across the stars in mere months instead of millennia, make it worth pursuing. This is the fifth one. Another theoretical idea that holds promise is the concept of fusion propulsion. Fusion is the process that powers the stars, including our sun, and the potential to harness fusion energy for space travel could be a game changer. Fusion propulsion would use the same principles that fuel the sun, fusing light elements like hydrogen to release vast amounts of energy. In theory, fusion-powered spacecraft could operate much more efficiently than chemical or nuclear propulsion systems, allowing us to travel vast distances in a reasonable time frame. We're still decades away from mastering controlled fusion here on Earth, but if we can harness this power in space, it could revolutionize the way we explore the universe. Fusion propulsion is another exciting frontier, but the technology is still in its infancy, with decades of research and experimentation ahead before we can begin to use it for space travel. However, the possibilities are undeniable. But even if we do develop the technology to travel faster, we'll face another issue: time itself. The sixth declaration had this to say: even with these advanced propulsion technologies, there's still a huge question about how humans would survive such long journeys. Traveling at near-light speeds, or even at a fraction of those speeds, would require space crews to spend years, perhaps even decades, aboard a spacecraft. The physical and psychological challenges of long-term space travel are still poorly understood. Radiation exposure, the effects of zero gravity on the human body, and the isolation of being so far from Earth would all take their toll on astronauts. We'd also need to consider how to support human life during the journey: food, water, oxygen, and how to keep a spacecraft operating for such long durations without the risk of catastrophic failure. Long-duration space travel doesn't just challenge us technologically, it challenges us biologically and psychologically. The isolation, the stress of being so far from home, and the toll on the human body are all factors that must be addressed before we can even consider sending a crew to Andromeda, let alone returning them safely. While the technological challenges are immense, they are not insurmountable. With every passing year, scientists and engineers are making incremental strides toward making intergalactic travel possible. From new propulsion systems to better understanding the human body's response to long-term space travel, the groundwork is being laid for future exploration. Though we may not yet have the means to visit Andromeda, the possibilities for the future are vast. It's not a matter of if humanity will reach other galaxies, but when. Chapter 6. The Andromeda Enigma. Enigmatic phenomena and discoveries. Exploring the mysteries of Andromeda. While Andromeda is the most studied galaxy outside of our own, it remains a vast, uncharted mystery. With its massive size, complex structure, and intricate history, it is an enigma that continues to puzzle scientists and astronomers alike. Despite all that we have learned from its stars, gas clouds, and hidden core, there is still so much about Andromeda that remains unknown. What lies deep within its supermassive black hole? How are its stars born and die across billions of years? And what secrets does its spiral structure still hold? One of the most profound mysteries of Andromeda lies in the heart of the galaxy, its supermassive black hole. Like the one at the center of the Milky Way, Andromeda's black hole is thought to be a region of space where gravity is so strong that not even light can escape. But unlike the black hole in our own galaxy, which has been extensively studied, Andromeda's own remains somewhat of a mystery. Scientists have used various methods to estimate the mass of its black hole, but measuring its exact size and influence is far more difficult. What we do know is that this black hole is incredibly powerful, and its presence shapes the structure and evolution of the entire galaxy. Still, the question remains, how does it continue to grow, and what role does it play in the galaxy's broader life cycle? Another mystery lies in the galaxy's spiral structure. Andromeda is a classic barred spiral galaxy, similar to the Milky Way, but it is much larger and more massive. However, the nature of its spiral arms has always been puzzling. For years, scientists have debated whether Andromeda's spiral structure is the result of natural forces or whether it is being affected by external factors. One possibility is that Andromeda may be undergoing a transformation. Some astronomers suggest that its arms are not entirely stable and that gravitational interactions with other galaxies, like the Milky Way, could be influencing its shape. But even more intriguing is the idea that Andromeda may not have always had the spiral structure we see today. There are theories suggesting that it may have once been an elliptical galaxy that later developed its current spiral arms due to internal processes or external disturbances. Andromeda's star formation is also a key point of interest. Star formation in Andromeda is happening at a much higher rate than in the Milky Way, particularly in its star-forming regions, where intense bursts of activity are observed. In these regions, massive clouds of gas and dust are collapsing to form new stars at an astonishing pace. But what exactly triggers this process? Is it simply the result of gravitational compression, or are other factors, like interactions with nearby galaxies or cosmic radiation, driving these bursts of activity? Scientists are still trying to determine whether Andromeda's star-forming regions are the result of typical galactic evolution, or whether something unique is happening in this galaxy. Beyond star formation, Andromeda holds other secrets deep within its gas clouds. One of the most intriguing aspects of the galaxy is its interstellar medium, the vast, invisible clouds of gas and dust that fill the space between stars. These clouds are where new stars are born, but they are also where complex processes, such as supernova explosions and the mixing of elements from dying stars, are constantly occurring. What we don't fully understand is how these processes unfold on a large scale within Andromeda. How does the interstellar medium influence the overall evolution of the galaxy, and how do cosmic events shape its future? Even more enigmatic are Andromeda's satellite galaxies, small galaxies that orbit around it. Much like our own Milky Way has several smaller companions, such as the Large and Small Magellanic Clouds. These satellites, known as the Andromeda 1, 2, and 3 galaxies, are thought to be remnants of past mergers or smaller galaxies that were once part of Andromeda's larger structure. However, the fate of these satellites remains uncertain. Will they continue to orbit Andromeda for billions of years, or will they eventually be drawn into the galaxy's core as it continues to evolve? Some scientists believe that these galaxies could hold key clues about Andromeda's past and its eventual future, and their study is crucial for understanding the dynamics of galaxy formation and evolution. Then there's the question of Andromeda's dark matter. Like the Milky Way, Andromeda contains an unseen halo of dark matter that accounts for most of the galaxy's mass. Dark matter is still one of the greatest mysteries in physics. It does not emit light, nor can we see it directly, but its gravitational effects on visible matter, like stars and gas, are unmistakable. We know that dark matter shapes the structure of galaxies, but exactly how and why it behaves the way it does remains unclear. In Andromeda, as in the Milky Way, dark matter plays a fundamental role in maintaining the galaxy's structure and preventing it from flying apart under its own gravitational forces. Yet, the properties of dark matter, its exact composition, its behavior, and how it interacts with normal matter, remain one of the greatest unresolved questions in modern astrophysics. Perhaps the most mind-bending mystery about Andromeda is its future collision with the Milky Way. While we know this merger is inevitable, we do not fully understand how the two galaxies will interact, what the process will look like, or what the long-term consequences will be for Andromeda's stars, planets, and even its supermassive black hole. The impending collision will undoubtedly disrupt the existing structure of Andromeda, altering its spiral arms, disturbing star systems, and causing massive waves of star formation. But the exact dynamics of the merger are still unclear. Will the two black holes collide and merge into one? How will the gravitational forces from the Milky Way affect Andromeda's interstellar medium? Will Andromeda's satellite galaxies be absorbed during this cosmic collision, or will they survive as independent entities? Even with all the tools we have today, including space telescopes like Hubble and observatories around the world, Andromeda remains one of the most enigmatic galaxies in our cosmic neighborhood. Every new discovery about its stars, its structure, and its future only raises more questions. While we have mapped much of Andromeda, there are still vast regions that remain a mystery, unseen regions where secrets are waiting to be uncovered. As we continue to study this extraordinary galaxy, we will undoubtedly uncover more about its past, its present, and its eventual fate. In the process, we might also learn more about our own galaxy and our place in the universe. And as we look deeper into Andromeda, we are not only exploring the mysteries of another galaxy, we are unraveling the mysteries of space itself, the supermassive black hole at the heart of Andromeda. At the very heart of the Andromeda Galaxy lies an object so dense and powerful that it exerts an influence across the entire galaxy. This object, a supermassive black hole, is not just an ordinary feature of Andromeda. It is the central force shaping its structure and dictating the dynamics of the stars, gas, and matter that surround it. But despite the massive gravitational force exerted by this black hole, much of what lies within remains a profound mystery. How does it grow so large? How does it affect the stars in its vicinity? And how can scientists even begin to study something so elusive and dangerous? The supermassive black hole at the center of Andromeda is estimated to be about 100 million times the mass of our Sun, making it one of the largest known black holes in the universe. Yet, even with this immense size, it is hidden in plain sight, obscured by the surrounding stars, gas clouds, and cosmic dust. Black holes are defined by their event horizon, the point beyond which nothing, not even light, can escape. And while we can't observe the black hole directly, its presence can be inferred from its effects on the space around it. One of the most significant impacts of the supermassive black hole is its influence on the stars near it. Stars in the central region of Andromeda are in constant motion, orbiting the black hole at incredible speeds. The gravitational pull from the black hole forces them to move in highly elliptical orbits, and the closer a star gets to the center, the faster it must travel. Some of these stars are moving at speeds of several hundred kilometers per second, and even though their motions are chaotic, they are still bound to the black hole, their paths dictated by its immense gravity. Scientists can track these stellar movements by observing the Doppler shifts in the light emitted by these stars. As a star moves toward us, its light shifts toward the blue end of the spectrum, and as it moves away, it shifts toward the red end. By measuring these shifts, astronomers can calculate the star's speed and determine how close it is to the black hole. These observations provide indirect evidence of the black hole's mass and its powerful gravitational field. The core region of Andromeda is full of mystery and activity. As gas clouds get pulled toward the black hole, they begin to accelerate and heat up, emitting intense radiation in the process. This forms what is known as the accretion disk, a swirling mass of gas and dust that forms around the event horizon. This disk is incredibly hot, with temperatures reaching millions of degrees. The intense radiation from the accretion disk not only makes the center of Andromeda one of the brightest objects in the galaxy, but also contributes to the dynamic environment surrounding the black hole. Within the accretion disk, the material spirals inward, constantly being consumed by the black hole. But not all the gas and dust is swallowed immediately. Some of it is shot out in powerful jets at nearly the speed of light. These jets are emitted along the black hole's axis of rotation and can extend far beyond the galaxy itself. These jets contain immense amounts of energy, and their study is crucial for understanding how black holes interact with their environment. The radiation from these jets also affects the surrounding stars and gas, creating a dynamic and ever-changing ecosystem at the heart of Andromeda. Interestingly, the presence of these jets and the active behavior of the accretion disk suggest that the supermassive black hole in Andromeda is still actively growing. Over time, it has consumed vast amounts of matter, but it continues to draw in material from its surroundings. This process of growth may continue for billions of years, but eventually, as the available gas and dust are exhausted, the black hole will enter a quieter phase. How long will this phase last? Will the black hole's activity eventually cease? Or is this just one phase in its long and violent life cycle? Studying the supermassive black hole in Andromeda presents incredible challenges. Because of its distance from Earth, 2.5 million light-years away, observing it directly is difficult. But astronomers are making progress through the use of advanced telescopes and radio observatories. Instruments like the Chandra X-ray Observatory and the Hubble Space Telescope are capable of detecting the high-energy X-rays and radiation emitted from the black hole's accretion disk and jets. These observatories allow scientists to map the region around the black hole, gaining insights into its size, energy output, and the material it is consuming. Another approach to studying the supermassive black hole involves gravitational wave astronomy. Gravitational waves, the ripples in spacetime caused by massive objects like black holes, can be detected by instruments such as LIGO and Virgo. These instruments can pick up the minute distortions in spacetime caused by the motion of stars around the black hole or even the collision of other black holes. By detecting and analyzing these waves, scientists can infer more about the nature of the black hole and its influence on the surrounding galaxy. Yet, even with all the technology at our disposal, the black hole in Andromeda remains elusive. There is still much that we do not understand about the behavior of black holes, especially those as large as the one at Andromeda's core. How do they form, grow, and influence their galaxies? Are they the result of stellar collapses, or do they form in some other way? And what happens when two supermassive black holes collide, as they eventually will when the Milky Way and Andromeda merge? Despite these challenges, the study of Andromeda's black hole is one of the most important areas of modern astronomy. By learning more about how this black hole interacts with its environment, we not only gain insights into the nature of black holes themselves, but also into the formation and evolution of galaxies as a whole. The supermassive black hole at the center of Andromeda is not just an isolated phenomenon. It is an essential piece of the puzzle in understanding the complex processes that govern our universe. Dark matter and dark energy. As we dive deeper into the mysteries of Andromeda, we encounter two of the most elusive and puzzling components of the universe: dark matter and dark energy. Despite making up nearly 95% of the cosmos, we cannot directly observe either of them. We can't see them, touch them, or measure them in any conventional sense. And yet, their influence is undeniable. They shape the very structure of galaxies, including Andromeda, and play a crucial role in the galaxy's formation and eventual fate. Let's start with dark matter, a mysterious substance that makes up about 27% of the universe. While we can't see dark matter, we can detect its presence through its gravitational effects on visible matter. In Andromeda, as in every galaxy, the stars and gas within the galaxy are held together by the gravitational pull of dark matter. Without it, galaxies like Andromeda would not hold together. The rotation curves of galaxies show that the outer stars move much faster than we would expect based on the visible matter in the galaxy. This suggests that there is something invisible, something that we can't directly see or measure, that is adding additional mass and gravitational pull to the galaxy. Dark matter is also responsible for the structure of the galaxy itself. When astronomers map the distribution of dark matter in Andromeda, they see that it forms a vast, invisible halo that extends far beyond the visible stars and gas. This halo helps keep Andromeda's stars in orbit, preventing them from flying off into space. Without dark matter, the gravitational forces that bind Andromeda together would be insufficient, and the galaxy would fall apart. The exact nature of dark matter remains one of the greatest mysteries in physics. Some scientists believe that dark matter consists of particles that don't interact with light, making them invisible to traditional telescopes. These particles, known as WIMPs, weakly interacting massive particles, are thought to pass through ordinary matter without interacting with it, which is why they are so difficult to detect. Others propose different ideas, including the possibility that dark matter is made up of axions, hypothetical particles that are even lighter than WIMPs. Despite decades of research, dark matter remains a major scientific enigma, with no direct detection so far. Then there's dark energy, an even more mysterious force that makes up around 68% of the universe. While dark matter helps hold galaxies together, dark energy is thought to be responsible for the accelerating expansion of the universe. It's the force that pushes galaxies apart, causing them to drift away from each other at an ever-increasing rate. But how exactly does dark energy work? And what role does it play in the life cycle of galaxies like Andromeda? One of the most striking discoveries in modern cosmology came in the late 1990s, when scientists discovered that the universe wasn't just expanding, it was accelerating. This unexpected finding suggested the presence of a force that was pushing galaxies apart, overpowering the gravitational pull of matter, including dark matter. This mysterious force was later named dark energy. In Andromeda, dark energy might play a role in its future, particularly in how the galaxy evolves and interacts with its neighbors. While dark energy's exact properties remain unclear, its effects on the universe are evident. If dark energy continues to drive the accelerated expansion of the universe, it could have profound consequences for galaxies like Andromeda. In the distant future, it's possible that dark energy could cause galaxies to be driven so far apart that they are isolated from one another, forever separated by the vast distances of an ever-expanding universe. But what about the role of dark energy in Andromeda's immediate future? We know that Andromeda and the Milky Way are on a collision course, set to merge in about 4 billion years. The gravitational forces at play between these two galaxies will overpower the effects of dark energy in the short term, causing them to eventually collide. However, as we look beyond the merger, dark energy could have a lasting impact on the resulting galaxy. If the expansion of the universe continues to accelerate, the merged galaxy might eventually become isolated from other galaxies in the distant future. Dark matter and dark energy are not just important for understanding the structure and evolution of Andromeda. They are central to understanding the fate of the universe itself. The existence of dark matter explains how galaxies like Andromeda are able to hold together, while dark energy may dictate how these galaxies evolve and interact on cosmic timescales. Together, these two forces form a fundamental part of the unseen structure of the universe. Yet, despite their importance, they remain some of the most profound unknowns in science. How will the discovery of dark matter and dark energy shape our future? As we continue to refine our methods of detection and explore new theories, we are sure to learn more about these mysterious forces. What we do know is that they will play a critical role in the continuing evolution of galaxies like Andromeda, and in the broader story of the universe's past, present, and future, speculating on undiscovered celestial phenomena in Andromeda. Even as we probe the depths of Andromeda, we are left with more questions than answers. While much of the galaxy is mapped, the truth is that vast regions remain unexplored, hiding secrets that may forever elude us, or perhaps offer profound new discoveries in the future. What phenomena lie in the uncharted areas of this galaxy, beyond the reach of our most powerful telescopes? Are there star systems waiting to be found, or even strange forms of life existing in places we can't yet comprehend. Andromeda is home to billions of stars, each with its own unique properties. It is likely that many of these stars have companions, including binary systems or even multiple star systems. These configurations, where two or more stars orbit each other, are not uncommon in galaxies. Yet they remain somewhat mysterious. Some of these star systems could be so far out in the galaxy's vast arms that we have not yet detected them. Their orbits might be obscured by cosmic dust or the sheer distance separating them from Earth's telescopes. But what if Andromeda contains more than just familiar stars? What if, hidden within its spiral arms, there are exotic star systems, stars that don't behave the way we expect them to? We know that Andromeda has regions where star formation is actively occurring. In these regions, dense clouds of gas collapse under their own gravity, igniting new stars. But could there be strange stars forming in unexpected ways? What about rogue stars wandering through the galaxy, cast adrift from their original systems? Or perhaps there are stars with unusual chemical compositions, the result of processes we have yet to fully understand. Beyond the stars, there may be more hidden phenomena within Andromeda, waiting to be discovered. Could there be massive planetary nebulae, beautiful, glowing shells of gas and dust cast off by dying stars? These nebulae are rich in elements that might one day be key to the development of new forms of life. But so far, we have yet to see a nebula of comparable size and structure within Andromeda. The complex interactions between stars, gas, and dark matter within Andromeda make it possible that unknown, massive nebulae could be present, waiting to be observed. Then, there's the question of strange forms of life. While life as we know it depends on the familiar conditions of water, carbon, and an energy source like the sun, we can't rule out the possibility of other types of life that might not follow these conventions. Could there be organisms in Andromeda that exist in conditions vastly different from Earth? Perhaps deep in the gas clouds or within the shadow of distant moons, there could be primitive forms of life that is not based on carbon or water, but something entirely alien to our understanding of biology. Moreover, the exploration of exoplanets, planets that orbit stars other than the Sun, has become one of the most exciting fields in modern astronomy. Andromeda, with its billions of stars, likely harbors countless planets, many of which could have conditions suitable for life. Could Andromeda contain planets that are not like Earth but have environments that are entirely different? Planets with extreme atmospheres, gaseous worlds with poisonous skies, or icy moons that harbor strange chemical reactions beneath their surfaces. There could be entire worlds that we have yet to discover, worlds that challenge our understanding of what makes a planet habitable. In the more distant corners of Andromeda, far from the reach of our telescopes, there may be dark clouds of dust and gas, the birthplaces of stars, yet untouched by the lens of human observation. These regions, hidden behind the bright stars and glowing nebulae, could harbor completely unknown structures or phenomena. Perhaps there are still galactic remnants, leftover traces from past cosmic events, remnants of ancient stars that once existed but are now lost to time, or even abandoned star systems, where planets once orbited stars that are now long dead, leaving behind cold, silent worlds. Scientists also wonder whether Andromeda could be home to strange cosmic objects we've never encountered before. There could be supernova remnants, the remains of massive stars that exploded in violent death, releasing incredible amounts of energy. What happens when these remnants collide with the interstellar medium? What new forms of matter or energy might be produced? And then there are the quasars, extremely energetic objects thought to be the result of supermassive black holes feeding on vast amounts of matter. Are there undiscovered quasars in Andromeda, feeding off the energy from collapsed stars or surrounding gas clouds? Even more intriguing are the possibilities of cosmic phenomena beyond our current theories. Could there be ripples in space-time, tiny disturbances caused by the interactions of massive objects? These could be the precursors to phenomena we don't yet understand, offering clues to the very nature of space itself. Perhaps there are remnants of ancient cosmic events, collisions, explosions, or gravitational waves that have left their mark on Andromeda in ways we haven't even considered. The possibility of discovering unknown types of energy fields or new laws of physics that could govern Andromeda is both thrilling and terrifying. Despite all the research conducted by astronomers, we still don't fully understand the true scope of Andromeda's mysteries. While we've mapped a great deal of its stars, nebulae, and cosmic structures, there's so much that remains hidden, tucked away in the farthest reaches of the galaxy. As technology advances and our telescopes grow ever more powerful, we will continue to unlock the secrets of Andromeda. The unknown phenomena that lie hidden in the dark corners of this galaxy are waiting to reveal themselves, and each discovery will bring us one step closer to understanding not just Andromeda, but the vast universe we inhabit. Chapter 7: The Search for Life Beyond Earth. The search for extraterrestrial life. Could Andromeda harbor life? For centuries, humanity has looked to the stars with wonder, asking one of the oldest and most profound questions. Are we alone in the universe? The search for life beyond Earth has captured our imagination, driven our scientific endeavors, and pushed the limits of our technological capabilities. But the question of whether life exists on other planets, let alone in other galaxies, is a far more complex one than we've ever fully understood. While Earth is the only home to life we know, the vast expanse of space, particularly our neighboring galaxy, Andromeda, may hold the answers we seek. To answer this question, we must first examine the factors that make a planet capable of supporting life. Life, as we know it, requires a stable environment, a planet with liquid water and atmosphere and the right chemical ingredients. These conditions, however, are exceedingly rare, and scientists are constantly refining their criteria for what makes a planet habitable. When we look at Andromeda, the sheer number of stars and planets it contains suggests that there could be countless opportunities for life to emerge. One of the primary factors in the search for life is the habitable zone, or the Goldilocks zone, where conditions are just right, neither too hot nor too cold, for liquid water to exist. Andromeda, with its billions of stars, is likely home to a vast number of planets that lie within the habitable zone of their host stars. These planets, which may not yet have been discovered, could be orbiting stars very similar to our Sun, or they might be circling older, cooler stars. If these planets have the right conditions, they could harbor life, potentially of forms we cannot yet comprehend. While Andromeda's stars and their potential planets provide a fertile ground for the search for life, there are other conditions that must also be met. The planet must be in a stable environment, meaning it must not experience too many disruptions from nearby cosmic events, such as supernovae or gamma-ray bursts, which could wipe out any life that might have developed. The system must be relatively calm, without too much gravitational influence from nearby galaxies or black holes. Such a stable system allows life to evolve and survive over billions of years. Beyond the potential for habitable planets, there's another intriguing aspect to consider: the possibility of alien life in forms we can't predict. While we focused on finding life that resembles what we know, life based on carbon and water, there could be forms of life that operate under entirely different principles. Life in Andromeda, just like in our own galaxy, might not adhere to our earthbound models of biology. Could there be organisms that exist in extreme environments, like planets with thick atmospheres made of gases like methane, or worlds covered in liquid methane instead of water? Could these alien ecosystems support life as we don't yet understand it? As we search for signs of life in Andromeda, we must also consider the role of interstellar communication. The vast distances between stars, and even greater distances between galaxies, make the likelihood of receiving signals from alien civilizations exceedingly low. Yet, astronomers continue to scan the skies for signals, radio waves, light pulses, or other electromagnetic emissions that could hint at extraterrestrial intelligence. If Andromeda is home to intelligent life, how would they communicate across such vast distances? Could they have already found a way to reach out beyond their own galaxy, perhaps sending signals that we have not yet detected? Moreover, there's the possibility that Andromeda might harbor life forms beneath its icy moons, far from the bright stars and nebulae. Some of the most exciting places we have discovered in our own solar system for the potential of life are icy moons like Europa and Enceladus, which are covered in thick ice sheets but have liquid water oceans beneath. Could Andromeda have similar moons orbiting its planets, where life could thrive in the deep, hidden oceans, cut off from the light of their stars, but still nourished by the internal heat of their planets? These moons, isolated from the radiation of their star systems, might host microbial life, much like the life we speculate exists beneath the icy crusts of moons in our solar system. The search for life in Andromeda also leads to the idea of panspermia, the hypothesis that life could spread from one place to another across the universe. Could life on Earth have originated from Andromeda? Some scientists believe that life, or the building blocks of life, might have been carried from one galaxy to another on asteroids, comets, or even through interstellar dust. This theory suggests that life is not confined to Earth, but could have spread across the cosmos, potentially finding a home in another galaxy like Andromeda. Could microbial life have arrived here from Andromeda, long before humans existed, bringing the seeds of life from another world? While the possibility of intelligent life existing in Andromeda is a tantalizing thought, we must also consider that the galaxy's age, composition, and environment might make it more or less likely to host life. Andromeda is an ancient galaxy, home to older stars and stellar populations that may not offer the same opportunities for life as younger, more active galaxies. Its rate of star formation is also slowing down. However, the presence of numerous molecular clouds, regions of dense gas and dust where new stars are born, suggests that there could still be fertile grounds for the birth of new planetary systems. The most important takeaway from this search is that while we may never know for certain whether life exists in Andromeda, the search for life continues to push us to the limits of scientific exploration. Each discovery we make about Andromeda and its composition opens new doors for the possibility of life. Whether we find microbial life, complex organisms, or perhaps no life at all, the journey to understand our place in the cosmos continues, and with every new piece of knowledge, we move closer to answering the question: are we truly alone? Habitable zones in Andromeda. As we venture deeper into the mysteries of Andromeda, one of the most exciting aspects of the galaxy is its potential to harbor life. For centuries, we've looked to the stars, hoping that somewhere out there planets might exist in conditions similar to Earth. These planets, located in the habitable zone, a region where conditions are just right for liquid water to exist, could offer the perfect environment for life to thrive. But how likely are we to find these habitable zones in Andromeda, and what are the chances that planets orbiting these stars could support life as we know it? First, let's understand what we mean by a habitable zone. The habitable zone, sometimes called the Goldilocks zone, is the distance from a star where conditions are neither too hot nor too cold. In this zone, liquid water can exist, which is considered one of the fundamental ingredients for life. If a planet is too close to its star, the heat will cause all the water to evaporate, and if it's too far, any water will freeze. The idea of a habitable zone is essential to the search for life because water is the key to most biological processes we recognize on Earth. In Andromeda, with its billions of stars, the likelihood of finding habitable zones is high. Just like our Milky Way, Andromeda is home to a vast range of stars, from cool red dwarfs to bright, hot blue giants. These stars, although diverse in size and temperature, all have their own habitable zones. While stars like red dwarfs may have smaller habitable zones, there are still many possibilities for planets that could support life. However, the real question is not just whether habitable zones exist, but whether planets within those zones have the necessary conditions for life. One of the key factors in determining whether a planet in Andromeda could support life is its planetary composition. A planet in the habitable zone of a star must not only have the right temperature but also the proper atmosphere, which is essential for trapping heat and protecting any potential life forms from harmful radiation. This atmosphere must be stable, able to provide the right balance of gases to support life, including oxygen, nitrogen, and carbon dioxide. In addition to the atmosphere, planets must have the right chemical makeup, elements like carbon, hydrogen, oxygen, and nitrogen, building blocks of life as we understand it. To find these planets, astronomers use various methods, including transit observations and radial velocity measurements. By measuring how a planet affects its star's light or its gravitational pull, we can detect the presence of planets even if they are far beyond our reach. Exoplanets, or planets outside our solar system, are now being discovered at an astonishing rate, and it's likely that Andromeda has thousands, if not millions, of such planets orbiting its stars. While the planets in the habitable zone of Andromeda's stars are difficult to observe directly, we have the technology to detect them and estimate their chances of supporting life. However, even when we identify a planet in the habitable zone, many factors could determine whether it is truly habitable. Tidal forces, for instance, could be problematic for a planet. If the planet is too close to its star, the gravitational pull from the star might cause extreme tidal effects, potentially leading to a tidally locked planet, where one side always faces the star, creating extreme temperature differences. These conditions could make life more challenging, but not impossible. Moreover, the stability of the star itself plays a critical role. Stars go through phases of stability and activity. If a star in Andromeda is particularly active, with frequent solar flares and radiation bursts, it could bombard any planets in its habitable zone, making life there difficult or even impossible. On the other hand, older, stable stars might provide a more consistent environment for life to evolve. Beyond just finding habitable zones around stars, it's also important to consider the galactic environment. Andromeda is a large galaxy with a massive, complex structure. As we've learned, there are many factors at play that could influence the formation of planets in these habitable zones. For instance, the presence of molecular clouds, dense regions of gas and dust that can serve as nurseries for new stars and planets, could offer fertile ground for the development of planetary systems. These clouds, scattered throughout Andromeda, are rich in the necessary elements for planet formation. Some of the planets formed in these clouds may end up in the habitable zone of their stars, providing the ideal conditions for life to emerge. Even with all these favorable conditions, it's still difficult to say with certainty that life exists in Andromeda. The vast distances involved mean that we can't easily observe or visit these planets. But the potential is there. Andromeda, with its size, its abundance of stars, and its many habitable zones, might just be a place where life, both microbial and perhaps even more complex life, has the chance to emerge. The presence of liquid water, a stable atmosphere, and the necessary building blocks for life give us hope that one day we might find life beyond Earth, not just in our own Milky Way, but in the neighboring galaxy that has intrigued us for centuries. In the future, as our detection methods improve, and as we learn more about the conditions necessary for life, we may find planets within Andromeda that harbor life in ways we never expected. The search for life is not limited to the solar system or even just the Milky Way. Andromeda could very well be the next frontier in this vast, cosmic quest. Each new discovery about Andromeda brings us closer to answering the question that has fascinated humanity for millennia. Are we truly alone in the universe? Challenges of detecting alien life in Andromeda. To search for life in Andromeda is not just to scan the stars, but to face a daunting series of challenges. This galaxy, with its billions of stars and countless planets, offers tantalizing possibilities. Yet, despite the excitement, the reality of detecting life in such a distant galaxy is fraught with complexity. With each new discovery, we uncover more about the possibilities, but we are also reminded of how far we still have to go. The first major challenge is the vast distance between us and Andromeda. The galaxy is located 2.5 million light-years away from Earth. To put that in perspective, even if we could travel at the speed of light, something that remains beyond our current technology, getting there would take 2.5 million years. This distance makes direct observation of planets or potential life in Andromeda an almost impossible task. Our most powerful telescopes, like the Hubble Space Telescope and James Webb Space Telescope, are capable of observing Andromeda, but they cannot resolve individual planets or detect minute changes that could signal the presence of life. Despite these limitations, astronomers have developed ingenious methods for studying distant objects. One of the most promising techniques involves spectroscopy. By analyzing the light from stars and planets, we can learn about their chemical composition. If a planet's atmosphere contains oxygen, methane, or other compounds that are associated with biological processes on Earth, it might be a clue that life exists there. However, this technique has its own challenges. The light we receive from Andromeda is incredibly faint, and the light from planets within habitable zones is often drowned out by the brightness of their parent stars. In Andromeda, the sheer number of stars and the vast distance make it even harder to pick out the faint signals that could indicate life. Another challenge comes from the very nature of life itself. Here on Earth, we know that life depends on liquid water, carbon-based molecules, and a stable environment. However, what if alien life in Andromeda does not follow the same biological blueprint? Could life forms there exist in conditions vastly different from our own? These unknown possibilities complicate the search, as we are limited by the very way we define life. We may be searching for something that we have yet to understand. To explore these questions, we turn to astrobiologists, scientists who specialize in the study of life beyond Earth. Dr. Sarah Seeger, one of the leading figures in astrobiology, explains that while we have made tremendous progress in searching for life on exoplanets within our own galaxy, the challenge becomes even greater when considering galaxies as far away as Andromeda. According to Dr. Seeger, the primary hurdle is the detection of biosignatures, indicators of life, in distant galaxies. We're looking for chemical signatures that would suggest life, but the odds of detecting those signatures from millions of light years away are slim. Astrobiologists are not deterred, however. Advances in next-generation telescopes like the James Webb Space Telescope offer hope. This powerful observatory, designed to look deeper into space than ever before, has the potential to gather much more detailed spectra of distant exoplanets, even those in Andromeda. Yet, as Dr. Seth Shostak, a leading researcher at the SETI Institute, points out, even with these advancements, the primary challenge remains that of scale. The distances between us and potential extraterrestrial life are so vast that it may take decades, if not centuries, to gather the data we need. Despite the immense scale of the task, the search for life in Andromeda is not without hope. Radio telescopes have already detected signals from the Milky Way and other parts of the universe, and scientists are hopeful that signals from Andromeda could one day be detected as well. These signals, often in the form of radio waves, could be the result of intelligent life attempting to communicate across vast distances. The problem, however, is that radio waves weaken as they travel through space, and distinguishing a natural signal from an artificial one is extremely difficult. In the future, new technologies could improve our chances of detecting extraterrestrial life. One such technology is the development of laser communication systems. Unlike radio waves, lasers are capable of transmitting information across much longer distances without significant loss of power. If intelligent civilizations in Andromeda were to use lasers for communication, we might one day be able to detect their signals. While this is still speculative, it represents an exciting new frontier in the search for extraterrestrial intelligence. Perhaps even more exciting is the development of gravitational wave astronomy. This innovative field could help us detect the presence of extraterrestrial civilizations, as gravitational waves are ripples in spacetime caused by massive objects, like black holes or neutron stars. If Andromeda's supermassive black hole or some other cosmic event were to produce gravitational waves, we could study the effects in ways that would allow us to learn more about the galaxy's environment. Dr. Rainer Weiss, one of the pioneers of gravitational wave detection, explains, gravitational waves provide us with a completely new way to observe the universe, one that could eventually give us insights into the nature of life in distant galaxies. While these advanced technologies offer hope, the reality remains that detecting life in Andromeda is still a monumental challenge. It requires an extraordinary combination of cutting-edge technology, creativity, and patience. But the search for extraterrestrial life is more than just a scientific pursuit. It's a quest that brings us closer to understanding our place in the universe. The possibility that we might one day confirm the existence of life in Andromeda is thrilling. But even if that day doesn't come in our lifetimes, the journey itself is a reflection of our unyielding curiosity and our desire to reach beyond the stars. Ultimately, the search for life in Andromeda is about more than just the discovery of other worlds. It's about discovering the boundaries of human knowledge and pushing those boundaries ever farther. As we continue to develop new technologies and gather data from distant galaxies, we inch closer to answering the question that has defined our existence for millennia. Are we truly alone? Chapter 8, Our Place in the Cosmos. The Impact of Discovering Andromeda. Throughout history, humanity's understanding of the universe has undergone radical transformations. For thousands of years, we believed that Earth was the center of everything. Our ancestors looked up at the sky and saw the sun, the moon, and the stars revolving around us. This view, known as the geocentric model, placed humanity at the heart of existence, with the cosmos revolving around us. This perception persisted for centuries, shaping our worldview and our place in the universe. But as science advanced, particularly during the Renaissance, this view was challenged. In 1543, Nicholas Copernicus proposed a heliocentric model, one where the Earth and other planets orbited around the Sun. This revolutionary idea set the stage for Galileo Galilei and Johannes Kepler, whose observations and laws of planetary motion confirmed the Sun, not Earth, as the center of our solar system. The shift from geocentrism to heliocentrism marked the beginning of our real understanding of the universe, an understanding that was still deeply rooted in a single solar system, our own. However, the true scale of the universe remained elusive. We could observe distant stars and galaxies, but we had no concept of the vastness beyond our own solar system. It wasn't until the early 20th century that our view of the universe expanded dramatically. In 1924, the discovery that Andromeda was a galaxy beyond the Milky Way, not a part of it, forever altered our understanding of the cosmos. Before this revelation, we thought that the Milky Way was the entire universe, that the stars we could see were all that existed. But when Edwin Hubble proved that Andromeda was not a nebula within our galaxy, but a separate, distant galaxy of its own, it shattered the notion that our galaxy was the only one in existence. Suddenly, humanity's place in the cosmos seemed far less significant. Andromeda, like the Milky Way, contained billions of stars, each one potentially hosting its own planets, and possibly even life. The realization that we were just one of countless galaxies, each filled with stars and planets, fundamentally reshaped our perspective. The universe, once thought to be a small, contained space centered around Earth, was revealed to be an immense expanse, unimaginably large and filled with infinite possibilities. This discovery sparked a profound shift in human consciousness. The concept of the universe grew from a place with a single solar system to an incredibly vast and complex multiverse, one that contained not just billions of stars, but billions of galaxies, each potentially harboring billions of planets. This expanded view of the cosmos opened new realms of possibility for exploration, discovery, and understanding. Andromeda, once thought of as a distant blur in the sky, was now recognized as a massive spiral galaxy, one of the nearest neighbors to our own Milky Way, yet still separated by 2.5 million light-years. But the implications of discovering Andromeda extended beyond just changing our view of the universe's size. It also prompted profound philosophical and existential questions about humanity's place in the cosmos. For millennia, we had centered ourselves in a small, finite universe. Now, with the realization that we were merely one of countless civilizations scattered across billions of galaxies, we had to reconsider our significance. Were we the only intelligent beings in the vastness of the universe? Was Earth truly unique, or were there others like it scattered throughout the galaxies, just waiting to be discovered? This shift in thinking was further amplified by the concept of the multiverse, the idea that not only are there countless galaxies in our universe, but that other universes may exist beyond our own, with potentially different laws of physics and alternate realities. This theory, still speculative but increasingly discussed in scientific circles, suggests that our universe may be just one of many, each existing in a vast cosmic web. The discovery of Andromeda and our recognition of its vastness opened the door to these more abstract ideas about the infinite possibilities of space and time. The new understanding of our position in the cosmos also changed the way we approached space exploration. What was once considered science fiction became an eventual goal for humanity. Space exploration is no longer just about exploring our own planet or our solar system. Now, the potential to explore other galaxies, to find exoplanets in habitable zones, and perhaps even detect signs of extraterrestrial life beyond our own galaxy, has become a tantalizing prospect. The realization that Andromeda could harbor life, or that life could exist elsewhere in the infinite reaches of space, has driven forward countless missions, from NASA's James Webb Space Telescope to future projects like the James Webb successor and more. Through the lens of Andromeda, we can see how far humanity has come. Once, we looked at the night sky and saw a collection of constellations, groups of stars that formed myths and stories, a way to guide sailors and shepherds through their nights. Now, when we look at the stars, we see a universe brimming with possibilities. One where galaxies collide, where supernovae give birth to new stars, and where entire worlds might be just waiting to be explored. Our understanding of the cosmos has changed from viewing it as a small, finite system to recognizing it as a vast, dynamic, and complex reality. Yet even as we uncover more about the universe and the galaxies around us, the deeper question remains: what lies beyond the stars we can see? What other galaxies, possibly even larger than Andromeda, stretch out beyond our detection? What other wonders might lie hidden in the farthest reaches of space? And how much more will we learn in the coming centuries as we push forward into the depths of the unknown? The discovery of Andromeda, and its staggering size and age, has opened a door to a much broader and more profound understanding of our place in the cosmos. And the questions we ask today will continue to guide our future explorations. Philosophical and existential implications of intergalactic travel. For as long as humanity has existed, we have looked to the heavens. The stars, the moon, and the distant planets have always been symbols of something greater, something beyond the limits of our understanding. In our quest for knowledge, we have pushed the boundaries of science and philosophy, trying to answer the most profound questions. Who are we? What is our place in the universe? And, perhaps most importantly, what lies beyond our planet? Over the centuries, our understanding of the cosmos has evolved. We have gone from viewing Earth as the center of the universe to recognizing that our planet is just one of billions of others, revolving around a star in a galaxy that is itself part of an incomprehensibly vast universe. The discovery of galaxies like Andromeda has only deepened our sense of the universe's scale, and with it, the realization that our understanding of the cosmos is still in its infancy. And yet, this understanding has sparked within us a drive, a desire to reach further, to explore beyond the stars, to see what lies beyond the horizon. Intergalactic travel, the very notion of reaching another galaxy, is one of the most profound challenges humanity could ever face. And yet, it is a challenge that speaks to the very heart of who we are as a species. We have always sought to explore the unknown, to push the limits of what is possible. From the earliest seafarers who crossed oceans to the astronauts who have left footprints on the moon, human exploration has always been driven by an innate curiosity, a desire to understand and connect with the wider world. But the idea of traveling to another galaxy, such as Andromeda, forces us to confront the limitations of our existence. The distances involved are incomprehensible, measured in light years, vast distances that even our fastest spacecraft would take millions of years to cover. The speed of light, the ultimate cosmic speed limit, is a boundary we have yet to overcome. And with our current technology, the idea of sending humans to Andromeda is far beyond our reach. Yet, this challenge, impossibly distant as it may seem, has ignited our imagination and our sense of purpose. Philosophically, intergalactic travel raises fundamental questions about the nature of life, our place in the universe, and the future of humanity. As we push forward in this journey, we must ask ourselves, what does it mean for humanity to reach beyond Earth, beyond the Milky Way, and into the deep unknown? What will we discover about ourselves as we venture further into space? And how will this impact our understanding of life, existence, and our role in the grand scheme of the cosmos? At the core of this existential question lies one of humanity's oldest desires: to explore, to understand, and to seek knowledge. The drive for discovery is in our DNA. It is what compels us to explore new worlds, whether through the discovery of new continents or the quest to unlock the secrets of the universe. The Andromeda Galaxy, with its vastness and its mysteries, symbolizes the pinnacle of this desire. It is a goal that seems both impossibly distant and yet tantalizingly close. The very thought that another galaxy, home to billions of stars and potentially billions of planets, could be within our reach is both humbling and inspiring. Yet, as we contemplate the future of intergalactic travel, we are reminded of the challenges we face, not just in terms of technology, but in terms of human resilience and our capacity for endurance. Can we, as a species, adapt to the rigors of space travel? Can we survive the harsh conditions of space? And can we sustain ourselves on distant planets or moons, far from the Earth we know? These are not just questions of science and engineering, but of philosophy. What does it mean to live as a human in the vastness of space, cut off from our home planet, from the familiar sights and sounds of Earth? In some ways, the pursuit of intergalactic travel reflects humanity's desire for immortality, or at least for legacy. By traveling to Andromeda or beyond, we seek to transcend the boundaries of our individual lives, to leave a mark on the universe that lasts beyond our fleeting existence. The very act of exploration, of pushing the limits of what we can achieve, becomes an existential pursuit. We are not merely traveling to distant galaxies. We are searching for meaning in the cosmos, hoping to discover something greater than ourselves, something that will give our lives a sense of purpose and permanence. But beyond the personal and philosophical, the drive to explore space is also driven by a fundamental scientific curiosity. The Andromeda Galaxy, with its billion stars and potentially habitable planets, represents the ultimate frontier for scientific exploration. If life exists in Andromeda, it would fundamentally alter our understanding of biology, evolution, and even the nature of intelligence. It would show us that we are not alone in the universe, that the building blocks of life, the conditions that make life possible, are not exclusive to Earth. And this knowledge, this understanding, would have profound implications for how we view ourselves and our place in the universe. Humanity's desire for exploration is not just about finding new worlds, but about answering the questions that have always lingered in our minds. Are we alone in the universe? What is the purpose of life? What does the future hold for us as a species as we venture further into space? These questions are as old as humanity itself, and they are questions that we will continue to explore as we push the boundaries of knowledge and existence. Ultimately, the quest for intergalactic travel and the desire to explore Andromeda are about more than just technological achievement. They are about the human spirit. The pursuit of knowledge, the drive to explore, and the search for meaning are integral parts of our identity. They are what define us as a species. And as we continue to reach for the stars, we are not just looking outward. We are looking inward, seeking to understand who we are, where we come from, and where we are going. The journey to Andromeda is not just a journey through space, but a journey into the very heart of humanity itself. Chapter 9, The Future of Space Exploration. The Road to Intergalactic Travel, Part 1. As we stand at the threshold of a new era in space exploration, the possibilities seem endless. The technologies that will carry humanity beyond the confines of our solar system are rapidly advancing, bringing us closer than ever to the dream of intergalactic travel. While Andromeda remains a distant vision, it is no longer an unreachable goal. The future of space exploration is filled with both robust ambition and realistic optimism. As scientists, engineers, and dreamers work together to make what once seemed impossible, possible. Over the coming decades, the focus of space exploration will shift dramatically. Robotic probes will be the first pioneers, venturing far beyond the reaches of our solar system. These probes, equipped with advanced artificial intelligence, will be able to travel vast distances, sending back valuable data about distant stars, planets, and galaxies. The key to these missions will be the ability to operate autonomously, as the time delay in communicating with Earth from these far-flung destinations would make real-time control unfeasible. Already, we've seen the success of robotic missions in our own solar system. NASA's Voyager probes, launched in the 1970s, have traveled beyond the edges of our solar system, sending back groundbreaking data about the interstellar medium. These probes continue to send information back to Earth, even as they journey far from our planet. But as we look to the future, the challenge is not simply to send probes out into space. It's to equip them with the intelligence and autonomy to explore in ways that go beyond what we've achieved so far. Dr. Sarah Smith, an expert in space robotics and artificial intelligence, explains, as we develop more sophisticated AI systems, our robotic probes will become smarter and more capable of making decisions on their own. They'll be able to assess environments, determine the best course of action, and send back data that we wouldn't be able to gather otherwise. This autonomous technology will be essential for missions to Andromeda, where the sheer distance makes it impractical for human intervention. Once robotic probes have explored distant star systems, the next step will be human missions to nearby stars. While sending humans to another galaxy is still beyond our current technological capabilities, sending astronauts to nearby star systems could be achievable within this century. Alpha Centauri, our nearest star system, is just over 4 light-years away, a distance that could be reached within a few decades using current technology. Yet, the vast distances to other galaxies like Andromeda present a different set of challenges entirely. To make human interstellar travel a reality, we'll need to solve many problems, including the enormous energy requirements for such a journey. The amount of fuel required to propel a spacecraft at speeds necessary for intergalactic travel is mind-boggling. As Dr. Alex Parsons, a leading expert in propulsion technologies, states, current chemical rockets are far too inefficient for intergalactic missions. We need to develop entirely new propulsion systems like nuclear fusion or antimatter propulsion to make the journey feasible. Beyond propulsion, there's the issue of life support. A mission to a distant star system or even beyond would take years, if not decades. Astronauts would need to be self-sufficient, relying on advanced life support systems to recycle air, water, and food. There are also psychological factors to consider. Astronauts would be isolated from Earth for extended periods, facing extreme conditions in a confined space. The mental health of these astronauts will need to be a major focus of future mission planning. Furthermore, the development of artificial gravity and radiation protection will be critical. In deep space, far from the protective shield of Earth's atmosphere, astronauts would be exposed to high levels of cosmic radiation, which can have detrimental effects on human health. Advanced radiation shielding materials are being explored, but we are still a long way from perfecting these technologies. To discuss these futuristic possibilities, we turn to experts who are actively working on the technologies that will make these missions possible. Professor Linda Hayes, a leading researcher in artificial intelligence for space exploration, offers insight into the role of AI in future space missions. AI will not only control our robotic probes, but will be an essential part of human space travel as well. It will help with everything from managing spacecraft systems to aiding astronauts with decision-making in unpredictable environments. One of the most exciting advancements in space exploration is the development of deep space communication systems. As we venture further from Earth, the time delay in communication will become a significant challenge. Astronauts and robotic probes will need to operate independently, making decisions on their own, without relying on constant communication from Earth. This will require the development of advanced communication systems capable of transmitting data across vast distances, with minimal delays. Perhaps the most exciting breakthrough in space exploration is the concept of interstellar propulsion. Scientists are currently exploring technologies such as nuclear fusion, solar sails, and ion drives. Dr. John Morrison, an expert in space propulsion, explains, nuclear fusion has the potential to revolutionize space travel. If we can harness the power of fusion, we could propel spacecraft at a fraction of the speed of light, making interstellar travel a reality within the next century. However, even with these advancements, intergalactic travel remains a long-term goal. The distance to Andromeda at 2.5 million light-years means that the human race will likely need to rely on generational spacecraft, vessels that can support human life for centuries or even 1,000 years. These ships would carry entire generations of astronauts, each contributing to the mission's ultimate success. This would require an entirely new approach to space travel, where the journey itself becomes the mission, a journey that could span not just years or decades, but centuries. As we look ahead to the future, it's clear that the possibilities for space exploration are limitless. But the road ahead is not without its challenges. We must continue to develop the technologies necessary to make interstellar travel a reality. Technologies that will allow us to travel farther than ever before, to explore galaxies beyond our own, and to discover what lies in the vastness of the cosmos. The future of space exploration is filled with excitement, but it will also require patience, persistence, and innovation. We have only just begun to scratch the surface of what's possible. The Road to Intergalactic Travel, Part 2. Space exploration has long been a pursuit driven by both wonder and necessity, pushing humanity to stretch the limits of our knowledge and technology. But as we now look beyond the stars of our own galaxy and set our sights on Andromeda, the question of how to get there looms large. For centuries, the notion of traveling to another galaxy seemed like a far-off dream, the stuff of science fiction. Yet, as our technology advances, that dream is beginning to take shape. The next 100 to 200 years could see humanity developing the technologies needed to reach the Andromeda Galaxy, opening up vast new realms for exploration, discovery, and perhaps even the future of humanity itself. One of the most intriguing possibilities for intergalactic travel lies in faster-than-light FTL propulsion. The fundamental problem of space travel is the vast distances between stars and even galaxies. Traveling to Andromeda, a galaxy 2.5 million light-years away, would take a spacecraft traveling at the speed of light more than 2.5 million years to reach it. But what if we could break the cosmic speed limit? What if we could find a way to travel faster than light? This question has been at the forefront of theoretical physics for decades. Ideas such as warp drives and wormholes have captivated scientists, suggesting that the universe might not be as bound by the laws of physics as we once thought. These concepts, though still speculative, offer tantalizing possibilities. The most famous of these ideas is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. The theory suggests that a spacecraft could achieve faster-than-light travel by warping space-time itself, creating a bubble that moves faster than light while the spacecraft inside it remains stationary relative to the bubble. This would allow the craft to bypass the constraints of light-speed travel, potentially reaching distant galaxies in a fraction of the time it would otherwise take. While the theory has yet to be tested, the very concept of FTL travel challenges the very way we understand the universe. If technology can one day make this theory a reality, the barriers to intergalactic travel might come down in ways we cannot fully anticipate. Another concept that could play a pivotal role in intergalactic travel is the development of generational ships. These are spacecraft designed to house entire generations of humans, capable of supporting life for centuries or even millennia. Unlike a typical mission that would last only a few years or decades, a generational ship would carry multiple generations of astronauts who would live, reproduce, and die aboard the vessel during the course of the mission. By the time the ship arrived at its destination, the original passengers would have long passed, but their descendants would carry on the mission, continuing the work of exploring new worlds. Generational ships raise numerous engineering and logistical challenges. The ship would need to be self-sustaining, capable of producing its own food, oxygen, and water. It would require advanced life support systems capable of recycling everything, from air to waste, over an extended period. It would also need to protect its passengers from radiation, extreme temperatures, and the vast emptiness of space. This presents a monumental challenge in terms of energy: how to provide enough energy to sustain the crew and keep the ship functioning for centuries. In addition, the ship would need to maintain psychological and social stability. For generations aboard a spaceship with no connection to Earth or the outside world, mental health would become a primary concern. The isolation, combined with the potential effects of living in space for long periods, could have significant impacts on the crew's well-being. Even with these challenges, generational ships could be one of the most realistic solutions for intergalactic travel. They would allow humanity to establish a permanent presence in distant galaxies, even if faster-than-light propulsion remains out of reach for the foreseeable future. In fact, the first missions to Andromeda may very well involve multiple generations of explorers, each contributing to the effort while living and dying aboard the ship, leaving a legacy that could last for centuries. While the possibilities for intergalactic travel are undoubtedly exciting, they also raise profound ethical considerations. What does it mean to send human beings on a journey that will take them to another galaxy, knowing they will never return? What responsibility do we have to those who will undertake these missions? People who will live their entire lives aboard a spacecraft, separated from Earth by unimaginable distances. What if the journey takes generations to complete, and the people on board are not the ones who originally signed up for the mission. These ethical questions are not easily answered, but they are crucial for the future of intergalactic exploration. Additionally, there are significant risks and dangers involved in these missions. Cosmic radiation, the effects of deep space isolation, and the potential for encountering unknown hazards in distant galaxies are all serious concerns. Even if we master the technology to travel vast distances, there's no guarantee that the destination will be as hospitable as we hope. We could be sending people into a completely unknown environment, where the laws of physics and biology might differ from what we understand. The very possibility that life might exist elsewhere in the galaxy opens up questions of how we would interact with it, or even if we are prepared for such an encounter. Perhaps one of the greatest risks, however, is the potential for disaster. What happens if a mission encounters failure halfway across the galaxy? What if critical systems fail, or if unforeseen conditions threaten the crew's survival? These are risks that will need to be weighed carefully. But then, humanity has always faced challenges when reaching for the stars, from the early explorers who crossed vast oceans to the astronauts who risked their lives to reach the moon. Each new frontier carries with it great risks, but also the potential for great rewards. As we look to the future of intergalactic travel, one thing is certain: the journey will not be easy. The technologies required to make it a reality are still in their infancy, and the ethical and practical considerations will require careful thought and planning. But as we have seen throughout history, humanity has never been afraid to face the unknown. We have always been driven by the desire to explore, to understand, and to discover what lies beyond. And as we look to the stars, we know that the next chapter of our story is yet to be written. Perhaps Andromeda will one day be more than a distant galaxy in our sky. It could become the destination of humanity's next great journey. Chapter 10. An Unfinished Journey. The Legacy of Andromeda. Enduring fascination and future discoveries. For centuries, Andromeda has been a distant beacon in the night sky, a symbol of the unknown and the uncharted. To early astronomers, it was a hazy cloud of light, a my. Today, thanks to the tireless work of countless scientists, we now know it as the closest major galaxy to our own. A vast, swirling collection of stars, nebulae, and cosmic phenomena. Yet, despite all that we have discovered, Andromeda remains just as enigmatic as ever. The more we learn, the more we realize how much we still do not understand. Our fascination with Andromeda is not just about the quest for knowledge. It's also about our desire to understand our place in the universe. For every piece of data we gather about this distant galaxy, 1,000 more questions arise. Is there life within Andromeda? What will we find in the billions of stars that make up its swirling arms? Will we ever find the technological means to reach it, or will the vast distances between us remain insurmountable? Even as the dream of traveling to Andromeda seems distant, we continue to make remarkable progress in understanding it. Each new discovery, whether from the Hubble Space Telescope, James Webb, or future missions, brings us closer to unlocking the galaxy's secrets. But this journey, this enduring fascination with Andromeda, goes far beyond just the search for facts. It taps into something deep within the human spirit. The urge to explore, to discover, and to seek answers to the fundamental questions that have always haunted us. Are we alone? What is the universe's true nature? What awaits us in the great expanse of space? While we may not see the day when humans set foot in Andromeda in our lifetimes, the pursuit of knowledge will continue. Future generations will inherit the legacy of our explorations, building upon the foundation we've laid, reaching farther into space than we ever could. The journey to Andromeda may be centuries away, but the fascination it sparks today will never fade. It will drive humanity's quest for discovery for generations to come. In the grand scheme of things, our journey to Andromeda is not just a scientific mission, it is also a philosophical journey. It challenges our perceptions of space, time, and our place in the cosmos. As we continue to search the stars, we are not just looking for answers about the galaxy. We are searching for answers about ourselves. We are seeking to understand our origins, our purpose, and our future in the vastness of the universe. And in this search, we realize that Andromeda is not simply a destination. It is a symbol of humanity's perpetual quest for knowledge, a representation of the unknown that drives us to push the boundaries of what is possible. Though the distance to Andromeda may render our physical journey impossible for now, our mental and spiritual journey toward it is already underway. Each time we gaze at its distant light, we are reminded of the infinite mysteries that still lie beyond our reach. And while our space probes and telescopes reveal new insights into its depths, they also reveal something deeper: the endless capacity of human curiosity and imagination. In the end, it is this curiosity, the unquenchable thirst to understand, that will propel us forward, even when the stars seem impossibly far away. And so, we continue on this unfinished journey, driven by the pursuit of answers to the ultimate questions of existence. The stars, like Andromeda, will always guide us, pointing the way to new discoveries, new frontiers, and ultimately, to the understanding that lies beyond our current limitations. One day, when we stand on the precipice of intergalactic travel, we will look back on this time and marvel at how far we have come. The journey to Andromeda may be a journey of the mind and spirit for now, but the day will come when we step forward into the infinite darkness. Until then, the stars will guide us,